Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you today as it is every day here in my virtual classroom. Step on inside and we are in the Big Ideas Math Integrated Math 2 textbook looking at section 7.4, Properties of Special Parallelograms. We're talking about the rectangles, the rhombuses, and the squares. Yes, they are all parallelograms, and we're going to be talking about that quite extensively just as a reminder of how these things work. I'm going to start off with the lecture portion, then go to the problem set, up to 88 problems. I have no idea how long this is going to take. If lots drill and kill, we'll go ahead and take a look in a bit. But to remind you, if you want to try and follow along with me best as possible, jump to the description section down below. Go ahead and find a PDF of not only the attachment that I have here. I'll provide graph paper if we have to graph anything. I will provide timestamps for each individual problem that we have as well. So without further ado, guys, I'm going to go and get into it, and let's see what we have. Looking at this, we are going to, for properties of special parallelograms, use those properties here. We're going to use properties of diagonals of special parallelograms. Remember where they connect like boom, boom, diagonals, and use, looks like coordinate geometry, yes, to identify special types of parallelograms. So be ready for some graph bits. The rhombus, rectangle, and square are the core vocabulary of this one. Quadrilateral, parallelogram, and diagonal are from previous ones. So obviously very, very important. Okay, so here they are. Rhombus, well, they start with rhombuses. Rhombuses, rectangles, and squares. And the plural is rhombuses, not to rhombi. So a rhombus is a parallelogram with four congruent sides. So all four sides congruent to each other, not just the opposite sides congruent. Don't mistake that for a square. You do not need right angles for a rhombus to be what it is. Now, this is just their visual of it. If you ever want to see a rhombus in like a better way, tilt your head to the way that you get more of a diamond shape. More, like that. Just to get a bigger idea of what is also true about it. We're going to be talking about that specifically with diagonals. But that's one easier way to draw a rhombus, to get like, okay, this is congruent to that, and then this is congruent to that. They're all congruent to each other. And this is a rhombus as well, just the same way that they made a rhombus like that. Anyway, I was going to mention something else here about, and it's a parallelogram. It is a parallelogram with four congruent sides. What does a parallelogram have? Opposite sides parallel, and then it has a bunch of properties as well, and we'll dig into the whole what, how, why, and things like that of it later. All right, a rectangle is a parallelogram with four right angles. We know that shape very well. It's prevalent in all diagrams of anything that you ever do. Well aware of the name. You do not need all sides congruent, though. A square has both of those. It is a rhombus and a rectangle in that it has all four congruent sides and all right angles. It is a parallelogram with those things. So notice that they all define it with the word parallelogram. This is properties of special parallelograms, and so that, once again, is an important facet about everything else you're going to want to know about it. It's the best way to learn on what to know about these things. You can use the corollaries below to prove that a quadrilateral is a rhombus, rectangle, or square without first proving it's a parallelogram. So, as much as we just mentioned that they are parallelograms as far as defining them, and trust me, knowing that's important, those things do not need to be known in order for this stuff to be true. And in fact, there are proofs. Either we're going to prove it or the examples later are going to prove it. Rhombus corollary. A quadrilateral is a rhombus if and only if it has four congruent sides. If it's a rhombus, it has four congruent sides. If a quadrilateral has four congruent sides, it is a rhombus. Doesn't need to be stated to be a parallelogram before that. Doesn't mean it's not one. I'm just stating that there's that. A rectangle is a quadrilateral. A quadrilateral is a rectangle if it has all four right angles. And a square is, I keep saying it backwards. A quadrilateral is a square if it has four congruent sides and four right angles. Proofs on page 40. This is page 432, so I'm guessing that's in the problem set. We're going to have to prove them, and that's fine. They're all about triangle congruence, CP, all that kind of stuff's involved. Let me move myself over here, and let's take a look at what's next. The Venn diagram illustrates some important relationships for parallelograms, rhombuses, squares, and rectangles and squares. You can see a square is a rhombus because it's a parallelogram with four congruent sides. So stuff I talked about before, but take a look at this box thing. And if you know how Venn diagrams work, it's anything on the outside is not included with things, or includes everything on the inside. I'm saying it backwards. Everything inside this box is a parallelogram. Everything inside this circle is a rhombus. Because the rhombus is inside the box, it means a rhombus is a parallelogram. Oh, they did the diamond version of it as well, which is really good. A rectangle is a circle inside the parallelogram box. It's not in the rhombus circle except for a little part of it. And anything that's shared with a rectangle and a rhombus is a square, which is in the parallelogram box. These are all parallelograms. It's like whatever city you're in. I'm near the city of Sacramento. I'll just say, I'm in the city of Sacramento. That means I'm in the state of California. That means I'm in the United States of America. It means I'm in North America. It means I'm on Earth, right? Just kind of working in that way. Sacramento is a Californian property. It's a city. So you can imagine things that way. Okay, using properties of special quadrilaterals, let's take a look at some of these examples. For any rhombus QRST, and remember the order that it's stated matters, QRST, that means Q is connected to R and T, it's opposite S, things like that. Decide whether the statement is always or sometimes true. Draw a diagram and explain your reasoning. So here's a diagram that is drawn for QRST as a rhombus. We would know, we've only learned all sides congruent. Is angle Q congruent to angle S? Yes, because opposites, although we only learned opposite sides are congruent, we also learned it's a parallelogram. And in a parallelogram, opposite angles are congruent. This is what they're telling you here by the opposite angles theorem. So yes, always true. Angle Q congruent to angle R. In a rhombus, just like a parallelogram, consecutive sides are supplementary. So Q and R would add to 180 in an always case. Could they be congruent? They could be congruent if they were both 90-degree angles because, then they'd be adding to 180 still. You'd say, but Mr. Robinson, this is a square. Yes, but a square is a rhombus. A square is always in the rhombus circle. So all squares are rhombuses. This is, once again, one of those big conversations we're going to have. So this is sometimes true. If a rhombus is a square, if a rhombus has 90-degree angles, then angle Q is congruent to angle R. It's possible. You can't state how likely or not. That doesn't matter. For every square has that. So yes, sometimes true. And the sometimes cases honestly are the easiest ones to come up with because you can show a case when it does work and show a case when it doesn't work. And that's all you need. All right, classifying special quadrilaterals. Classify the special quadrilateral, explain your reasoning. So I see a 70-degree angle here, maybe of use, but I see all four sides congruent. Rhombuses have all four sides congruent, always. Not just by knowing it's a parallelogram or not. So this will be a rhombus by knowledge of this. Now they say the special quadrilateral, they do want you to be most specific, meaning if it was a square, they'd want you to name square. Don't say, but it's also a rhombus. We know that. Because I can also say, but this is also a parallelogram, but this is also a quadrilateral. Just most special rhombus, all four sides congruent. And they're actually mentioning, because one is not a right angle, it cannot be a square. I don't know if we need to mention that, but if it showed 90 degrees, we would. And yes, knowing just one of these was 90 would mean that, yes, it would be a square. All the other ones would actually follow form. Supplementary would mean the other half would be 90. Congruent means that one has to be 90. So that would work. Whoops, I went backwards. Let's go forwards. They're doing a proof, it looks like. Which proof are they doing? Hold on, let me change something here. Okay, use properties of diagonals. Oh, okay, so we're going to the diagonals of these things. Now, these have very important features for both rhombuses and rectangles regarding the diagonals. And this is where I said that diamond look will help you very well with it. This is where you can rotate your head and take a look. Rhombus diagonals theorem. A parallelogram is a rhombus if and only if its diagonals are perpendicular. Now, this is also something that the if and only if, by the way, means I could flip the thing. I could say a parallelogram is a rhombus if its diagonals are perpendicular, and I could also say a parallelogram whose diagonals are a diagonal has perpendicular diagonals if it is a rhombus. And those are only true. They are a one-to-one truth there. Any non-rhombus will not have perpendicular diagonals. Any perpendicular diagonals would not be a rhombus for parallelograms. Anyway, prove. Oh, I guess we're not proving it. Maybe we do. Is that? Oh, they're doing it here. Okay. So there's that one. Now again, if you rotate your head that way to see the diamond thing, you can really tell how those diagonals need to be perpendicular for the rhombus with the congruent sides. We need a certain symmetry. We'll prove it, but having that visual will give you a reminder. Also, opposite angles will be bisected. Okay. Diagonals bisect their angles. So diagonal bisects this angle. Diagonal bisects all those angles. We also know opposite angles are congruent. We know diagonals bisect each other in parallelograms. So here's the perpendicular one. So given that you have a rhombus, we know that we have congruent. They say AB congruent to BC, excuse me. AB congruent to BC, right there. And then they're going to, eventually they're going to use reflexive property here and here. Let's see where they go to next. Because it's a parallelogram, the diagonals bisect each other. So this would also be congruent to that. So now by side, 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 these two triangles here will be congruent. This ABE and this CBE. So by CPCTC, oh my gosh, sorry, I'm trying to mark this up. By CPCTC, you can then say that these two angles here are congruent. This guy, AEB and CEB. But they also form a linear pair. If congruent angles form a linear pair, they must both be 90 degrees. So that's what they're saying here. Two of the same angle that add to 180 must both be 90, right? Now, I have trouble writing that proof sometimes because I'm like, what do they need me to say? I said it out loud. Two of the same angle that need to add to 180 are both 90. If they're both 90, then they're both right angles. Therefore, boom, you got perpendicularity. Now, how far do you need to go with that? Any one thing that's known to be perpendicular here means all the others are perpendicular. The lines, excuse me, that's right angle. Any lines, I'm stumbling on my own words. The lines are perpendicular to each other if you know that you have one right angle. Okay, so I'm gonna erase that. There's the proof. So what do they say? If it's a parallelogram, if a parallelogram is a rhombus, yes. Okay, finding angle measures in a rhombus. This is where you start to do some of the math, solving for things, finding missing bits. We need to find angles 1, 2, 3, and 4 in this diagram. Well, I'll just call it out as I see it. They tell you it's a rhombus. They tell you it's a rhombus. So if it's a rhombus, angle 1 is going to be 90 degrees. We just learned that. Diagonals are perpendicular to each other. 1 is 90. 2, why is this 61? Because a rhombus is also a parallelogram. And in a parallelogram, opposite sides being parallel, you have two parallel lines cut by a transversal. I have alternate interior angles here and here. Alternate interior angles theorem tells you that. 3, why is 3 also 61? Because a diagonal bisects a rhombus. So this is congruent to that. Therefore, 2 is congruent to 3. 3 is also 61. 4, I can see a lot of ways to do it. They're talking about this triangle here specifically, because you already know that 1 is 90 and 3 is 61. So boom and boom. So 90 plus 61 is 151. Subtract it from 180, you get 29. You also didn't even really need the 90. 3 and 4 should be complementary and add to 90 themselves, but there's that. So those are the measures of the angles. You do need the degrees. Okay. Some examples of their own. We'll get our own. We have 88 problems to do. We'll have our own. Rectangle diagonals theorem. Now a parallelogram is a rectangle if and only if its diagonals are congruent. Knowing it's a parallelogram to begin with. Remember, keep that in mind. So, diagonals now congruent. Think about that. A parallelogram doesn't need congruent diagonals. They bisect each other, but not necessarily congruent. And as you stay a parallelogram and rotate things this way, now suddenly these diagonals are the same length. That means when they bisect each other, even these parts are the same together, right? Okay. Do they have examples? Yes, they do. You're building a frame for a window. The window will be installed in the opening shown in the diagram. So right here, the opening must be a rectangle. Given the measurements, given the measurements in the diagram, can you assume that it is? Oh, so we know that opposite sides are equal here and here. It doesn't seem like they say anything about right angles. So at the moment, I only see it as a parallelogram. Must be installed in the opening. So that's all I see right now. You measure the, let's answer. Okay, no, you cannot. The boards on the opposite sides are the same length, so they form a parallelogram, but you do not know whether the angles are right angles. Yes, so same thing. We don't know the right angles. They don't talk about diagonals, all that kind of stuff. B. You measure the diagonals of the opening. The diagonals are 54.8 and 55.3 inches. What can you conclude about the shape of the opening? Okay, so again, 54.8. 55.3, they're not the same. If they're not congruent, then it's not a rectangle. The if and only if says rectangles need congruent diagonals to be rectangles. Parallelograms need congruent diagonals to be rectangles. So this is not a rectangle. It's just a parallelogram. It's a poorly designed window. Okay, finding diagonal lengths in a rectangle. So in this situation, I should have moved a long time ago. In this situation, you have, knowing it's a rectangle, QS is the entire length, 5x minus 31. RT, this entire length is 2x plus 11. They want you to find the lengths of QRST. We know it's a rectangle, so we get to set those diagonals equal to each other. Boom, boom. And solve for x, you get 14. So then you can substitute 14 back in, and you can find the lengths. They should each be 39 when you plug them in. So take a look at the algebra from that. But again, rectangle has congruent diagonals. Set them equal. Okay, let's look at coordinate geometry. Identifying a parallelogram in the coordinate plane. Well, I think we did that before in section 7.3, maybe even 7.2. But identifying a parallelogram, what kind it is, rectangle, rhombus, square, if it's any of those. Give all names that apply. So basically, we want to do a lot. They're going to say understand the problem, make a plan. We want to understand what properties make those things true, and then start to build off same slope, opposite reciprocal slope, equal lengths. I'm probably going to do a lot less when it comes to things. Like I'll tell you about what they're doing here, and I'll tell you how I'm going to do it. But they're going to make a lot of distance formula stuff, slope y2 minus y1, things like that. But identify the type of parallelogram based on what you have. You graph the vertices, boom. If something's a rectangle, they go by the diagonals. They say if the diagonals are congruent, it's a rectangle. That's true. If you also have opposite reciprocal slopes, you have right angles. We can talk about that. If the diagonals are perpendicular, then it's a rhombus. You know what? I think I like their plan more. If they go straight from the diagonals only, then they can work it out. We already know it's a parallelogram. Congruent diagonals, rectangle. I gotta sneeze. Congruent diagonals, rectangle. Perpendicular diagonals, rhombus. Both, square. I have to sneeze again. Let me pause. Excuse me. Okay, so right here, I mean, listen, by appearance, I think we can say it's not a rectangle. And it's coordinate geometry. It's kind of drawn to scale. I don't see right angles. But is it a rhombus? Is kind of now the question. So from here, AC, they got a 6 root 2 using distance formula. I'm going to do more of a you go down 6 and right 6 kind of thing, which I can use Pythagorean theorem off of. And then this is 10 root 2 when all's said and done here from D to B. So not a rectangle, right? So they went off of those. But if you go off of slopes, the slope of AC is down 6, right 6. That's -1. And then slope of BD is up 10, right 10, and that's +1. Those are opposite reciprocal slopes. That means this is perpendicular here. So this parallelogram is also a rhombus. It's a parallelogram and a rhombus. I guess we don't have to say parallelogram because they know it's going to be parallelogram. They also say you can check the side lengths and see that everything is a rhombus by the length of 2 root 17. You can also check the slopes of 2 consecutive sides and see that they are not opposite reciprocals of each other, therefore not perpendicular, not a rectangle. That was the first thing I kind of brought up. Okay, guys, we're going to start some of these problems here with number 1 and 2, vocabulary and core concept check. Number 1, what is another name for an equilateral rectangle? They said rectangle, not quadrilateral, because rhombus could be a name, but a rectangle with all equal sides of a rectangle and then suddenly equilateral, all sides equal, square. This is a square here, okay? And I boxed it with a rectangle. Number 2, writing. What should you look for in a parallelogram to know if the parallelogram is also a rhombus? We have a couple things that we can look for here. So we can either look to see all sides congruent, or, here's the thing, or one pair of consecutive sides congruent, because you already know the opposite sides are congruent. But that's just the idea. Diagonals perpendicular to each other, and diagonals bisecting their angles. This is more of an or diagonals bisecting their angles. If any one of these things are true, then you do have a rhombus, knowing you have a parallelogram. If it's a quadrilateral, you need to find all sides congruent. Otherwise, that doesn't really work. Okay, guys, so we just got that thing started with those. Let's go ahead to the problem set, numbers 3 through 88. Can't say I'm always excited for that many problems, but if it's good drill and kill, then I am game. I want you guys to learn it. Go and check the description section down below. Find the timestamp for the problems that you want to dive into. We're going to go ahead and get started with problem number 3. In the set of 3 through 8, for any rhombus JKLM, decide whether the statement is always or sometimes true. Looks like never true. Draw a diagram and explain your reasoning. So Number 1, angle L congruent to angle M. Now, before I do anything, I want to make a drawing of this for a rhombus sake. And I don't know if I have a tool. I have a parallelogram tool. I don't know if I have one to make it exactly rhombus looking. Sure. If I rotate it, see, here's the idea I mentioned before. If I rotate it this way, then I could actually give myself a better chance of, is something a rhombus or not? Probably like that. But anyway, so here's my visual of a rhombus. Maybe I can copy paste it or something like that. But it's important to make the drawing for a couple reasons, not just the scale. Maybe next time I won't bother myself with the scale as much, but I call it J, K, L, M. Now, being a rhombus, we do know, sorry that I'm spending a bit of time on this. Being a rhombus, we do know that all sides are congruent. We also know that it's a parallelogram, so anything else about that would be true. Now, do I need to make that statement all sides congruent yet? I don't know. They're talking about angles. Angle L congruent to angle M. Angle L congruent to angle M. Here's L, here's M. Do they need to be congruent? Must they be congruent in a rhombus? No. In fact, they're only congruent. This is the same as one of the examples. They're only congruent if it's a square. So explain your reasoning. Sometimes, if it is a square. If it is a square. Because in this case, what we're looking at is, well, and they say draw a diagram to support your reasoning, right? Draw a diagram to explain your reasoning. So I drew a rhombus there. Let me draw it more square-like, knowing that a square is a rhombus, and then we'll kind of go off that next time. Sorry, it's my first time kind of seeing this kind of problem. So J, K, L, M, like that. So there's my best support kind of for something like that. And then boom, we got that also rhombus-like. All right, number 4. Angle K congruent to angle M. See, in the sometimes case, they're not congruent if it's not a square, if that makes sense. But angle K congruent to angle M. Well, this is always going to be true for a rhombus. So, again, getting back to my rhombus look. Sorry, I'm just going to keep it thick. J, K, L, M. Here's K and here's M. Okay, this is always true because a rhombus is a parallelogram. I don't remember the theorem name, parallelogram opposite angles theorem, or what have you. Also true of parallelograms. And a rhombus is a parallelogram. Okay. Number 5. Segment JM congruent to segment KL. I can tell you off the bat, as long as those are side lengths of this thing, this will be true. Just get ready to copy and paste that guy. All right, segment JM congruent to segment KL. Just lost my K and my M. So here's JM, here's KL. Not only is this always true, but I mean, anytime they're going to ask about segments of side lengths and things like that, this will be true of all rhombuses. So KL. So always. It's true for all rhombuses, true for all parallelograms. Definition of rhombus applies here. I feel like any segment ones we get to say that same thing. So let's just kind of get ready to copy and paste this. Number 6. JK congruent to KL. Exactly. So on this one here, JK and KL also side lengths. Let's kind of like bring this all over. Oh, that didn't all copy. Copy. There we go. The less I need to write, the better. JK congruent to KL. Boom. Definition of rhombus, once again, always true in that case. Another set of side lengths. No, these are diagonals. Number 7, JL congruent to KM. Well, JL congruent to KM. So in this set, let me just kind of draw it fast. So here's J, here's K, here's L, here's M. Now, currently, we're talking about the diagonals, this guy and this guy. And probably not very obvious. I didn't draw it very extreme, but KM is longer than JL in this case. right? If I go more extreme like this, clearly one diagonal is longer than the other. It's not a requirement for this to be true in rhombuses. Can it be true in rhombuses? Yes. My options are always or sometimes. There's no never case. In what case are these congruent diagonals? It's only in the case when that rhombus gets going this way. We learned that rectangles will always have congruent diagonals, but then that also means that squares must also have congruent diagonals, because every square is a rectangle, every square is also a rhombus. So it's the same kind of thing. If this is a square, it'll work out. We don't want to just say if it's a rectangle, because rectangles aren't rhombuses in every which case, right? So we don't really want to kind of jump into that name. But when they are one the same, then they are a square as well. So once again, JKLM for your rhombus. When is JL congruent to KM? If it's a square. So sometimes if square. Once again. And then number 8, angle JKM congruent to angle LKM. I have to take a look at where those are. So let's get a quick drawing. JKM. Oh, wait, JKLM. So it's diagonal based. Here's JKM right here. And here's LKM right here. That is true for your rhombuses. So angle JKM congruent to angle LKM. Yeah, rhombuses have diagonals bisecting the angles. So I don't know what the name was. Rhombus diagonal bisecting angle theorem. So yes, diagonals bisect angle theorem for rhombus, basically is what I'm saying. Always true for always. Oh, always, excuse me, not yes. Always. Okay. Really got to work on the handwriting when I'm trying to rush those ones. In examples 9 through 12, classify the quadrilateral, explain your reasoning. Can't guarantee that a rhombus is now or anything like that. We're also looking for parallelogram, rectangle, square. Now, I feel like everything here is at least going to be a parallelogram. I don't think we're going as more basic than quadrilateral. We'll see. But it sounds like when they call it special types of parallelograms that they will give us at least that much. All right, so on number 9, I guess there are markings. Okay, so I was gonna say I guess we just make assumptions on its appearance. If you can't tell, they're showing congruent side marks right here, but they also show congruent angle marks here. Now what's interesting is they don't show them as right angle congruent markings or right angle markings, but they do show them as congruent markings. If all sides, if all angles of a quadrilateral are congruent, and quadrilateral adds to 360, the interior angle sum, then all of them have to be 90 degrees. They don't show them as right angles, but they are right angles. So for number 9, without copying and pasting the image here, all sides congruent, rhombus, all angles congruent, all angles 90, rectangle, rhombus and rectangle make square. Square. Explain your reasoning. It is a rhombus and rectangle. Now, all sides 90, or all sides congruent, all angles 90 degrees. All sides congruent, all angles 90. Okay. So that's what we're getting into. A rectangle is both a rhombus and square, and then we have that. All right, number 10. It is kind of hard to see these visuals here. It almost looks like they have just single individual markings. I think this is doubly marked, like 2 congruent there, and these are congruent, and then they show a right angle right here. Now, by the opposite sides congruent, we could call this thing a parallelogram. Because we have a right angle featured, that means all the others are going to have to be right angles, because opposite sides congruent in a parallelogram, opposite angles congruent in a parallelogram, consecutive angles supplementary, and 90 plus what is 180? 90. So this will be a rectangle. You know what? I'm going to start typing these ones because I want to explain more with this. So this is a rectangle. So why? It's a parallelogram. It is a parallelogram by the converse of the opposite sides thing because of opposite sides congruent. And one angle marked at 90 degrees means all are right angles due to parallelogram properties. Again, opposite angles congruent, consecutive angles supplementary, 90-degree linear pair with supplementary with another one makes 180. The other one's 90. Excuse me, and I didn't even mark this as number 10 at the time. Okay, so that was number 10. Number 11. We have couple right angles. This is not very clearly marked, so hopefully you can kind of see some of it, but we have this drawn better than that, but couple right angles here. And then we have congruent markings there. This one's interesting because what do we know about it? So with these two sets of right angles, do the others have to be right angles? Well, not from an initial appearance, they wouldn't have to be, but because one of these could have been longer to make this kind of go this way. But they can't be longer because those opposite sides there are congruent. So what's more important here that we want to know is that when we have right angles here, they're not just congruent, but they're also supplementary, which means you also have parallel lines here. I know that I marked it the same color as what that was. It's not really good to see. That means these are parallel lines here. If you have parallel lines, we know that one pair of opposite sides, congruent and parallel, means you have a parallelogram. And then when you have right angles in your parallelogram, then you have a rectangle. So this is a rectangle. Rectangle. Opposite sides, one pair of opposite sides are parallel and congruent. Now, they were parallel for the right angles thing, making it a parallelogram. Because of the right angles, it is a rectangle. Remember, the last time we had a parallelogram with only one right angle, it was a rectangle. Two of them, forget about it. But we needed both of them to indicate that. And then number 12, we have number 12. We have 140, 140, and 40. Now, opposite angles are congruent here. Consecutive angles are supplementary here. And then all the angles would have to add to 360 if you want to figure out, Yeah, so opposite angles are congruent here. The markings of a parallelogram, not quite there. Consecutive angles here are supplementary. Definitely markings of a parallelogram because now you have some parallel lines. They'd have to add to 360. You have to find a lot of ways to figure out this is 40, or also figure out that you have some opposite sides parallel, which you'll have. But they also mark up this congruent and this congruent. Now, in a parallelogram, opposite sides are congruent, so this would have been congruent to this, but they show that consecutive sides here are congruent. So if this is congruent to this, and this is congruent to that, and these are all congruent to each other, we're making a rhombus. We also know it's not a square because it's not 90-degree stuff. So this is a rhombus. Okay, it's a rhombus because parallelogram is parallelogram, from what I said before, by given angle measures. And one pair of consecutive sides are congruent. Therefore, all sides are congruent. Now, the therefore, I was going to say all sides are therefore. They're congruent because I stated the parallelogram part. I'd go further and say in a parallelogram, opposite sides are congruent, that kind of stuff, but I'm just leaving it there. Okay, numbers 13 through 16. Find the measures of the numbered angles in rhombus D, E, F, G. Might be best that I copy and paste this diagram over. Okay. So number 13. Find the measures of the numbered angles. Okay, They don't say explain your reasoning, so I'm not going to write something out if I don't have to. So, measure of angle 1. Okay, we know that they say it's a rhombus. We know that in a rhombus, not just opposite sides congruent like that, which I'm not going to, or all sides congruent. We also know that a diagonal bisects its angles. So if this is 27, I'm going to tell you what else is 27. This, and this. Measure of angle 1 is 27 degrees. Diagonals bisect the angles of a rhombus. These are all 27. Measure of angle 2 will also be 27 for that reason. Measure of angle 3 is not 27, but it is 90. A diagonal is perpendicular, or diagonals are perpendicular to each other in a rhombus. Measure of angle 4 is 27, for the same reason all the other ones are 27 there. Now 5 and 6, they're going to be congruent to each other. Whatever one is, the other's going to be, just so you know. However, they are the other angles in the rhombus, so you have some options here. The long way is double 27 to get 54, and then do 180 minus 54 to get the angle set here and divide that by 2. Probably the shorter way is look within an individual triangle. You know, if this is 90 degrees, then so is that. This is 27 and 90, and these should add to 180. Or these two should just add to 90. So 90 minus 27 is 63. So these are each 63 degrees. Now, like I said, either method works just fine. But those are going to be the same for the same reason as before. Diagonals bisect the angles in a rhombus. Number 14. Let me get some of the marking of that 14 circle here in just a moment. Okay. Sorry about that little part. Okay. Number 14. Also a rhombus. Measure of angle 1. I guess we're not doing side lengths here. I guess that's too easy. 90 degrees. Diagonals bisect are perpendicular to each other. Measure of angle 2. We're going to base this off the 48 a little bit. Looks like we have to build. In fact, let me write these out because it looks like I want to get angle 4 first. And measure of angle 5. Okay, measure of angle 4 is also going to be, because I'm going to navigate this a little bit. It's going to be 48 degrees, like that guy. So this guy's 48 degrees here. Now, 5 was also then 48 degrees. Because remember, diagonals bisect the angles and opposite angles are congruent. So those are all 48, right? Like that. 2 and 3 will be the same thing. It's a lot like the previous problem. This being 90 degrees, you know, all these are 90 degrees like that. These add to 180, or these two just add to 90. 90 minus 48 is going to give you angles 2 and 3, because they're going to be the same then. So 90 minus 48 is 42. So 42 degrees for each of these. Quite a bit like the previous problem there. All right, 15 and 16, I believe, are a part of this set. So number 15 and 16, however, you only see a single diagonal. Does that make it easier or harder? Might make it a little bit harder because some of the angles were based off the 90 degree bit and then little triangles within there. We'll see. Okay, number 15, measure of angle 1. Well, I'll tell you what. We're talking about measures of angles 1 through 5. Well, measures of angles 1 through 4 are all going to be the same. I think we've seen that a couple times now. Opposite angles congruent, diagonals bisect those angles. Those bisected angles are all going to be congruent to each other. 1, 2, 3, and 4 are all the same. And actually, I want to answer 5 first. Opposite the 106 is 106. Now, you could do the whole, they all add to 360, like the whole quadrilateral interior angle things. Or just supplementary, 106. And I think that's really where I'm going to work this. 180 minus 106 gives you 74 degrees, which means any whole angle here, boom, is 74, and boom is 74, and we can divide that by 2. 74 divided by 2 is 37. So each of these are 37 off that front. What I could have also done was this, and I think it's probably less obvious, but it's the same exact math as this. You know, like these three angles add to 180, right? Measure of angle 1, measure of angle 4, and the 106. They add to 180. But in what we've established is these are all congruent. 1 is congruent to 4. So, I mean, if I just call these x's, x plus x like that, then solving an individual x would require 2 steps. What are they? Subtracting 106 and dividing by 2. So no matter what, you would still get to that set just by looking within the triangle, because what you have here is actually an isosceles triangle where 2 of the same angle measures are there. So that's an option, or the one we mentioned before about consecutive angle supplementary and working off that. Remember, math interconnects itself. It's not like, oh man, who knew? It's no, yeah, that's actually just a part of how maths. It's kind of nice. All right, on number 16 here, I'm copying the diagram over, but I also am having trouble not copying literally the number 16 there when I do it. So just, you're going to have a couple 16s in play. Okay, same-ish kind of thing, only this time the 1 isn't known like the opposite, and this is kind of here. So let's talk about our angles. Oh, not congruent. Measure of angle 1, 2, 3, 4, 5. Okay, measure of angle 1. I probably want to pocket that one for a second. Let's build some other ones. 2, 3, and 4 are all going to be congruent to each other with the 72. So they're all going to have the same angle measure here. 72. Now, this is the same form as the other one. You have 2 options to get 1 and 5, which, by the way, will be the same, right? Whatever 1 is 5 is. If this is 72, you can start saying, hey, these all add to 180, right? You're like, oh, now you're looking within the triangle. You weren't last time, were you? So 72 plus measure of angle 1 is 180, right? We're doubling the 72 for that. That's 144. Therefore, measure of angle 1 is 36 degrees. And so is measure of angle 5. So there's one option. What's the other option? It kind of now looks the other way here, that you can say 2 72s would be the entire angle here. That makes this 144. And then that is a consecutive angle with this one, which are supplementary in any rhombus, just like a parallelogram. That would also make this 36. What do you do for that? You multiply 72 times 2, double it, and then you subtract it from 180 to get 36. Same math, different approach. So it depends on what you're looking at. All right, number 17 to 22. For any rectangle W, X, Y, Z, decide whether the statement is always or sometimes true. Draw a diagram and explain your reasoning. So this time we know they're always rectangles, and the question is, sometimes it'll like, you know, is it a square, thing like that. So this is a lot like problems 3 through 8 for rhombuses. Now we're just more in rectangle land. So on number 17, angle W congruent to angle X. Let's first see where we are in this kind of diagram, WXYZ. So WXYZ. Remember, a rectangle has all congruent angles, all 90-degree angles like that already. That is a for sure. So angle W congruent to angle X in a rectangle? Always. That's part of the definition, man. Def of rectangle. And I'm not saying definitely of a rectangle. By definition of a rectangle, that is going to be true. It just is. And I'm sure I could explain some of those better with that, but that's how it's going to work. Now let's look at that same diagram, and then I can make my right drawing. WX congruent to YZ. So WX congruent to YZ. Now listen, a rectangle has certain properties that will always be true as well, but it's not its definition. Definition of a rectangle is the all right angles and all congruent and things like that. A rectangle will have opposite sides congruent. We know that because a parallelogram does that same kind of thing. So if I copied and pasted this, this is also always true of rectangles. Opposite sides congruent. It's a parallelogram property. So always opposite sides congruent, true of parallelograms. Again, I'm sure what the book would say is something like parallelogram opposite sides theorem, which is the better thing to say. It's probably would have been less to write, but I'm just stating that that's probably what you're looking for as an official answer. Number 19, WX congruent to XY. Before I draw it, let's take a look at where those would belong. WX congruent to XY. WX and XY are consecutive sides, like this one here. When is it true in a rectangle that consecutive sides are congruent? Like that? Because remember, a square will do that. A square will do it because a square is a rectangle. But then you get these all sides congruent thing, right? It's not just this here with opposite sides congruent. Suddenly that has to be congruent to that. Sometimes true if it is a square. Or a rhombus, right? But a rhombus rectangle is a square. If square. Remember, none of these are never, which I think they really want to just throw into the face of saying like, hey, we're going to look at, see these things here. We're not going to look at nevers. Number 20, WY congruent to XZ. This is about the diagonals now they're talking about. WY, segment WY congruent to segment XZ. In a rectangle, right? We're saying, hey, we got a rectangle. Can the diagonals be congruent? They are always congruent, yes. W, X, Y, Z, and these congruent here, always true of all rectangles. Always. This is a rectangle theorem. That diagonals are always congruent. Again, sorry if the reasoning is not well stated or well written, but I hope I'm stating it well enough. Number 21. Segment WY perpendicular to segment XZ. That is once again the diagonals. We've learned that remember, all these are parallel, well, they're all rectangles, but we learned that in all parallelograms, if the diagonals are perpendicular to each other, that'd be indicative in a rhombus. So in a rectangle, when you have perpendicular diagonals, you're looking also at a rhombus. But what is a rectangular rhombus? Or a rhombusal rectangle? A square. So in this case here, again, in this rectangle, we also have not just these perpendicular, but also WY perpendicular to XZ. This is what a square would have. And again, I don't know if that reasoning is best, but sometimes true if a square. Once again, because rhombuses take on that appearance. Okay. So again, probably not writing as much as I could for the reasoning, but stating it all is getting me there. Number 22. WXZ congruent to YXZ. Let's look where they are. WXZ, YXZ. Okay, so they want the case where, once again, in a parallelogram, we learned if the angles are bisected by the diagonals, then it's a rhombus. So this is the same kind of thing as the previous problem in just a different format here. If it's a square, it's true, but not because the perpendicular diagonals, because the diagonals bisecting their angles. So now we're looking at, hey, I got some bisected bits right there. Those are congruent. Sometimes. See, rectangles, let me find another rectangle here. This ain't congruent to that. This is clearly bigger than that is, and hopefully you can see that for what it is. So it's not always going to be true. But once again, if a square, and I keep saying if square, I'm saying a lot more with that though. If it's a square, it's also a rhombus. It's a rhombus because the diagonal's bisecting the angle, and that's not true of all rectangles. Only in the case of becoming a square is that true. Okay, and exercises 23 and 24 determine whether the quadrilateral is a rectangle. This time they do not tell you it is a parallelogram to work these things out here. So they only say quadrilateral. They say four-sided shape. We don't know opposite sides congruent, opposite sides parallel, diagonals bisecting each other. None of that. Only the markings they have is what we can go on. Is it enough to say it's a rectangle? So number 23. In number 23, they give you opposite angles congruent. That would be enough for a parallelogram. Okay, it's a parallelogram. Is there enough now to say it's a rectangle? Do we have congruent diagonals? Do we have any right angles here? No. So determine whether the quadrilateral is a rectangle. Not enough info. It's not saying it can't be. It's saying it doesn't must be. It mustn't be. So not enough info. It is a parallelogram. And remember, all rectangles are parallelograms, but not all parallelograms are rectangles. That's the important bit. Number 24. Okay, here we have 32 opposite sides congruent, 21 opposite sides congruent, indicative of a parallelogram. Then you have a right angle. Now, we've looked at this a couple times. Maybe it was the lecture portion, if not this, I don't know. Yes. They don't say explain. They just say determine. So I'm just gonna say yes. So again, parallelogram is true because opposite sides are congruent. That's a converse theorem of parallelograms. When you do have a right angle, then opposite that must be 1 because in parallelograms that's true. And then these are also going to be right angles because consecutive angles supplementary in parallelograms. So yes. Okay, number 25. In exercises 25 to 28, find the lengths of the diagonals of rectangle W, X, Y, Z. So this time we know it's a rectangle. We can draw this out. You know, they didn't draw this for us, right? So let's construct our own drawing here. Mean old people didn't draw it for us. W, X, Y, Z. Being a rectangle, one of the right angles here, we know diagonals are congruent. We know everything else that a parallelogram would say as well, which is opposite or diagonals bisect each other, da 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 da. So let's see what we're going to go off of. So those are congruent, right? Number 25, we have WY, which by the way is a diagonal. WY equal, 6x minus 7, and XZ equal 3x plus 2. Diagonal, diagonal, WYXZ. These are congruent to each other. Or we just find the lengths of the diagonals. I didn't know this was all about diagonals. So we're going to do more than solve for x. We're going to find the lengths of the diagonals. Subtract 3x from both sides and divide both sides by 3. Now for the lengths of the diagonals, WY and XZ, they're going to be the same length. I'll do 3 times 3 plus 2. 9 plus 2 is 11. So that's the ultimate answer for that one. So the WYXZ, WYXZ. Okay, so these are all about the diagonals. Now we know that for every future problem. I just got to still write out the information, but we know that it's all about diagonals setting them equal. This is true for all rectangles. WY is 14x plus 10. XZ. What I don't like is when they have x as a variable and x as a vertex. Angle label. So 14x plus 10 equals 11x plus 22. Subtract 11x, subtract 10, divide both sides by 3. WY and XZ are going to be the same length here. So there's a lot of redundancy in these guys. It's simple algebra, set them equal and solve. Unless there's something complex about the algebra that we have, like quadratics and fractions. So let's do 11. I'd rather do 11 times 4 than 14 times 4. Looks like that's 66. Those are long diagonals, I tell you. Number 27. Okay, WY. By the way, you didn't need to make the drawing. I didn't know what kinds of problems we were going to have here. They're all diagonal based, but it's nice to get the drawing to confirm what it is that you have. But like I said, you don't need the drawing if you know that WX, YZ, W, and Y are opposite each other in that way. So they do make diagonals. Okay, I get to add 18x to both sides to get 42x. I get to add 8 to both sides to get 21. See, I spoke too soon. Now we're going to have a fraction. Divide by 42. 21 over 42 reduces to 1/2. Okay, I know a lot of people like to say 0.5. There's nothing wrong with saying 0.5, but I'm going to keep it as 1/2. So WY equal to XZ. Let's take half of 24. 24 times 1/2 minus 8. That'll be 12 minus 8, which is 4. Last time we had really long diagonals. Now we have really short diagonals. I forget the diagonals of the other one already. 11, I think. And number 28. WY and XZ. Probably another fraction if we just ran into one before. Okay, So 16x plus 2 equals 36x minus 2. I'm going to subtract 16x to get 20. Add 2 to get 4. 20 divided by 4, or 4 divided by 20, excuse me, is 1/5. Oh, okay. So now we got to do, all right, wy equals xz. Remember, they are the same length. So let's do the 16. 16 times 1/5 plus 2. This is where, I'll be honest, probably better to work the decimal answer in this one here. We can work the fraction. I'll give you the fraction, and I'll give you the decimal equivalent. But 16 divided by 5 is 3.2. This time I'm actually going to write that. Plus 2, which is 5.2. So 5.2, but you can also do 26/5. Like that. 5 1/5. 5.2 works there. As long as it's exact, not bad to work off of there. All right. In numbers 29 to 34, name each quadrilateral, parallelogram, rectangle, rhombus, or square for which the statement is always true. Equiangular, equiangular. Okay, so I'm gonna type the answer bit, and I'll go from there. 29. Okay, these problems can get tricky with respect to, because there are some things that we're going to learn by, like, listen, if something is a square, that means it's a rectangle, and rhombus and quadrilateral and things like that. But this is more property-based, so this is more like, as long as it's true for one in the chain, then it should be true for all its other descendants. But not, like, all rectangles are parallelograms, but not all parallelograms are rectangles, things like that. So we really have to be careful on how we say those. However, we're looking more in terms of, does the property hold true for all those? So, like, it is equiangular. What kind of these? I mean, we should just do one at a time, really. We should just explore them and say which ones work. It is equiangular. A rectangle is always equiangular. All the rectangles are the same. A rhombus, no. A parallelogram, no. Not all equiangular. A square, yes, because a rectangle can become a square. So all that is a rectangle, all the equiangular ones can trickle down that way. So I think one of my case in point things is, if rhombus is an answer to one of my things, then square will always be an answer. If parallelogram is an answer to things, then all of them must be answers, because all of those are parallelograms. So I think I'm going to make sure that works. And if it's a square only, it's not a guarantee that all the other ones are, things like that. And I think number 30 is a case like that. So it is equiangular and equilateral. So in this case here, a rhombus is equilateral and a rectangle is equiangular, but I need to be both. Square is all that would be possible as a must in that case. It says always true. Which ones are always true? Square is always true for both of those. Number 31, the diagonals are perpendicular. So they're not stating, I have a shape with perpendicular diagonals as a quadrilateral. What shape must it be? They're saying, which among parallelogram, rectangle, rhombus, or square always has perpendicular diagonals? So we're really just looking, again, one at a time here. Diagonals are perpendicular. Not necessarily true for a parallelogram. Not necessarily true for a rectangle. Rhombuses always have perpendicular diagonals, and if a rhombus does, a square is a type of rhombus, then a square must always have that as well. So rhombus and square. So number 32. Opposite sides are congruent. Well, it's true for a parallelogram. So parallelogram can be made into a rectangle. A parallelogram can be made into a rhombus. And a parallelogram can be made into a square. So parallelogram is true. But guess what? Opposite sides are congruent in all rectangles, in all rhombuses, and all squares. Let me just back that up one, I guess. Up until that point. Looks good. Okay. So everything. Always true for all of them. The diagonals bisect each other. Also a true property of a parallelogram, therefore all the others. Right? I believe that should be working out just fine. Number 33. The diagonals bisect each other. I like that I can type these. Parallelogram, rhombus, rectangle, and square. And then number 34, the diagonals bisect opposite angles. Well, not doing a parallelogram, as in always, no. The diagonals bisect opposite angles. Not a parallelogram, not a rectangle. Rhombus, yes, therefore square. I was going to put therefore. That's why I have trouble, by the way, with these typo things. One, I'm typing around my microphone. Two, I'm saying things out loud as I type. I have trouble. I'm a pretty good typer. I know that it always looks like I have a bunch of typos when I go, and you're like, what are you doing? Trust me, I can type pretty fine in general. If I'm not speaking. All right, number 35. Quadrilateral PQRS is a rectangle. Describe and correct the error in finding the value of x. So in this situation here, they have PQRS as your rectangle. They stated that these are going to be the same measure, therefore x would be 58. Well, that would be true of a rhombus or a square. But a rectangle does not have diagonals bisect each other. So I'm going to type this one out as well. A rectangle. Okay, hold on. I'm going to say it, then I'm going to type it and try and prove something, even though I'm still typing around a microphone. A rectangle does not have diagonals bisect each other. Diagonals are only congruent to each other. But a rectangle is 90-degree angle measures as well. That's the other thing. So rectangle. Yeah. I'm not proving my point. Not diagonals. A rectangles. Ah! Okay. Let me do this on my laptop one day. I'll give you the 110 words per minute with 100% accuracy. Okay, so x plus 58, I'm just going to go straight off this, is 90. So x is 32. Okay, complementary. All right, number 36. Quadrilateral PQRS is a rhombus. Describe and correct the error in finding the value of x. So 36. Okay, so in number 36, they're saying that these are going to be the same measure here, which is, I can't think of any rhombus where that's ever going to be possible, actually. So they said these are congruent. No, 37, if these would both be 37, for example. This is its own unique angle camp with these ones right here. These are opposite each other in that kind of way. So, no, it's not 37. They're just basically mismatching angles. X and 37 and the angle, let's see, QRP and SQR are non-relatable, are non-congruent angles. In a rhombus, diagonals bisect each other, or their angles. But these are not a part of the same angle camp. Now, if you want to solve it, we'll work based off other rhombus properties. You have options. You can double 37 to get 74. You can know that this will be the supplement to 74, which is 106, and divide 106 by 2 to get 53. You could also note that in a rhombus, the diagonals form to make a right angle. So 37 and x are going to be complementary because these should add to 180. So those two would just add to 90. So 37 and x are complementary. X plus 37 is 90. I'm going the fast route, same like that one. And x is 53. All right. Okay, numbers 37 to 42. The diagonals of rhombus ABCD intersect at E. So they did call it a rhombus. Given that measure of angle BAC is 53 degrees, the length of DE is 8, and the length of EC is 6, find the indicated measure. I'm going to copy this over and paste it into my thing. Now, I do not know... Okay, yeah. I was going to say, I don't know if these problems are all interconnected. They are, because they're not giving you more information. They're just asking you to find more information. So it's already labeled. They do tell you it's a rhombus. So I'm going to mark some things up for us now. Congruent, right angle, congruent, congruent. I'm going to answer everything based off this right here. Diagonals bisect each other. Congruent, congruent. There's nothing that will be missed based off that. Here we go. All right. Measure of angle DAC. Number 37. Where's DAC? DAC is this guy right here. Congruent with the 53. It's 53. Number 38. Measure of angle AED. AED is this guy right here, 90. If that's 90, so are all the others. I only want one perpendicular sign there. Number 39. Measure of angle ADC. See, the tough part about what I'm sweating through right now is that I'm only going to be finished with 42, which isn't even half the problem set. And the later problems tend to get longer where you have proofs and stuff like that. These are really fast ones. Measure of angle ADC. All right, this is where we got to do a few more things. This is going to be based off the 53. Well, sort of. 53, 53, 90, 90. I'm going to work within the triangle and double it. No, I'm going to do this. 53. 53 times 2 is 106. I need all of ADC. This is 180 minus 106, which is 74. Whole thing is 74 for ADC. Half of it would have been 37, which is what I would have gotten with the 53 and the 90, the 37. Number 40, the length of DB. DB is the entire diagonal. Now, this diagonal's got bisected. If this is 8, so is that. So DB is 16. Double the 8. Number 41, the length of AE. AE is congruent with EC. EC is 6. AE is 6. Number 42, the length of AC. AC is the entire thing of AE and EC, so it is 12. Okay. There's that set. Like I said, still only halfway through. In exercises 43 to 48, the diagonals of rectangle QRST intersect at P. So 43. Given that measure of angle PTS, well, it's labeled, and QS is 10. QS is not labeled, but here's the thing. QS is the entire diagonal, so it's probably tougher for them to mark that up. Now, listen, there are things we can say on that, and I'm going to go ahead and write them in. I'm not going to do this. I'm not going to go, hey, this whole thing's 10. It kind of gets in the way. But it is a rectangle. It's a rectangle, which means the diagonals are congruent. But a rectangle is also a parallelogram, which means diagonals bisect each other. That means these are all 5. How do I know that? Because just one of them is 10. So divide it in half, and they're all the same. Those are all 5. That probably is going to answer some of the questions that they're going to ask, at least one of them. Number 43, measure of angle QTR. Now, I also didn't, I'm going to do more. Congruent, congruent, right angles. And those things are 5. Okay, measure of angle QTR. QTR. So 34 is one of 2 complementary angles for that right angle there. So 90 minus 34 will give me this guy. That's 56 degrees. And I'm going to write that right there. So number 43, boom. Number 44, measure of angle QRT. 44, angle QRT. Well, QRT, so it's this guy here. QRT is an alternate interior angle with STR right there. So they'll be congruent to each other. They'll both be 34. So this guy's also 34 degrees there. There are a lot of other ways you could come up with that, but I don't want to build all around this is 56 and this is alternate interior angles. Right? Rectangles are parallelograms, so we can still work that stuff off. Parallel lines. Measure of angle SRT. SRT. That's an alternate interior angle with this guy. One's 56, the other's going to be 56. So measure of angle SRT is 56 degrees because it was in the previous one. Or 43 at least. Number 46, 47, 48 are all lengths. The length of QP, well, that answers one of them, right, diagonal-wise. So length of QP is 5. Now, again, the way that I got 5 was this diagonal was 10, and diagonals in a rectangle are bisected, much like all parallelograms. Number 47, the length of RT. RT is the entire other diagonal. Diagonals are congruent to each other in a rectangle. If one is 10, then the other is also 10. By the way, this 5 was from 10 divided by 2. And number 48, the length of RP. RP is once again going to be one of those bisected diagonals, so it's also going to be 5. Okay. There's that. I'm going to pause for 1 second. Okay. Here we go. In exercises 49 to 54, the diagonals of square, oh, we get to talk about square. L, M, N, P intersect at K. Find the indicated measure. Measure. Given that LK, oh, LK is 1, and that is marked. All right, squares are so fun. Now, I mean, they are. They have everything involved. So square, we know. Right angles, we know congruent. Now, I'm here. I know everything of this shape that they're going to ask about and that I want to say. I want to kind of not give everything away just yet, but I am just going to mark just. Oh, hold on. Let me. Okay, I'll put congruence. I'll write ones after if need be. But okay, there's more that I want to say on this stuff, but I'll leave it. I know some of the ones that they're going to want to ask. All right, number 49, measure of angle MKN. Measure of angle MKN. And I know I'm probably giving away more secrets than I should there, but I still haven't given away everything. Measure of angle MKN. MKN is going to be 90 degrees because a square is a rhombus and yada, yada, yada. Number 50, measure of angle LMK. Let me know. LMK. All right, here's one of them secrets. See, I don't want to do this. I don't want to say, hey, this is bisected, boom, like that. But here's the thing. A right angle is bisected. A right angle is bisected. That means it's dividing its two congruent parts. This is going to be 45 degrees. That's a 45er right there. All of these little angles here are going to be 45. That's one of the little secrets I wanted to bring in to the fold. I knew it was going to be asked at some point. Measure of angle LPK, same thing, 45 degrees. It's very much like that. I'm not going to put it on the diagram, but LPK is also 45 degrees. This is this guy right there, LPK. This is for squares only that you're going to get all 45s. I think that's what I wanted to talk about on that one rhombus one where they said the 37. It's impossible for a rhombus to have 37 degrees here and 37 degrees here. That just can't happen in a rhombus. It's because they'd have to both be 45. Anyway. Number 52, the length of segment KN. Where is KN? KN is where I can now write this kind of stuff. These are congruent. So this is 1, so is that. So KN is 1. Come on, bring in the the big guns. We'll see if they're going to do it. Number 53, the length of ln. Well, ln is going to be that 1 plus 1. You get to double that. So ln, double the 1, double the fun. You get 2. Let's see if they ask the last one here. MP. Oh, they never did it. I was going to say something here. Number 54. Hold on. 54 MP. Listen, a square is also a rectangle. Diagonals are congruent to each other, so it's also 2. I mean, there's a lot we could do off that with the ones and ones. Here's what I thought they were going to do. I thought they were going to ask about a side length, LP, PN, something like that. And I was going to say the answer is the square root of 2. I thought they were going to have us use Pythagorean theorem, and they really should have. They should have had to use Pythagorean theorem because, look, it's a right triangle. Here's the right angle. So 1 squared plus 1 squared. And I'm like, they're going to reveal all the secrets. The side lengths of the square are the square root of 2 in this problem. They did not ask for it. Okay. In exercises 55 to 60, decide whether parallelogram, that's the symbol, JKLM, is a rectangle, a rhombus, or a square. Give all names that apply. Explain your reasoning. Now, there are a lot of ways, and use graph paper for this stuff, but there are a lot of ways that you can go about identifying these things because it's based off any of the properties that you do know and to make conclusions off of. However, the easiest ones when you have the diagram drawn, probably, especially based off the lecture portion, is to work off the diagonals. So J is at negative 4, 2. K is at 0, 3. L is at 1, negative 1. And M is at negative 3, negative 2. And keep in mind, they already told you that it is a parallelogram. I don't need to test for opposite sides parallel, opposite sides congruent, nothing of that sort. I also know that the diagonals are going to intersect at a midpoint together, all that kind of stuff. And yes, there are going to be some obvious, like this is not necessarily obvious as to whether this is a square or not, or rectangle or not, whatever. Like if I have this, I have no reason to ask myself whether that's a square or rectangle. You know what I mean? Or if I have if I have this, I'm not going to ask whether or not that's a rhombus. But this one here is everything is in question right now. I'll just go ahead and say that. Everything's in question. Now, the reason I bring up the diagonals comes twofold. Literally everything I do off of 2 little sets of counts is going to answer my whole question. The textbook stuff does a lot of distance formula, slope formula, based off the numbers. I want to go based off a count. I have a graph. I can use it. I want to go from J to L and figure out whether the length of segment JL is the same as length of segment KM and whether it's an opposite reciprocal to it as well. So here's going to be my test. I don't know if this is worth doing all the thin line stuff. I'm going to kind of thin a line through there, and I want to figure out this slope. Not just the slope, but the count. It goes down 1, 2, 3, and over 1, 2, 3, 4, 5. This tells me a lot of things. I'll let you know about them when I find out KM. From K to M also has a certain rise and run. The only problem is these are going to interfere with appearance. So, like, I'll change the color. Let's see what color I'm going to use. I'm going to use kind of a red. From M to K does this. So M to K, I rise 1, 2, 3, 4, 5, and I run 1, 2, 3. Okay, this tells me everything. I'm going to tell you what this answer is. It is a square, which means it's also all the other things. Why do I know that? They do say explain your reasoning. Why did I test diagonals? In a parallelogram, and we know it's a parallelogram, that's the big part. In a parallelogram, if the diagonals are congruent, it's a rectangle. Are these diagonals congruent? Yes. What are the diagonals' lengths? I don't know. I didn't calculate it yet. I just did it in my head. It's square root of 34. If I see, these are right triangles. I have a right triangle here, which means Pythagorean theorem, 3 squared plus 5 squared equals c squared, like that kind of thing. And then also right here. But if both of the right triangles have the same leg lengths, 5 and 3, then that means that the last side is going to be the same. So, JL is equal to km, which is the square root of 34. Where did I get 34 from, by the way? Like I said, 3 squared plus 5 squared. Here, that's 9 plus 25, which is 34. And take the square root of both sides. So each of the lengths are 34, but I don't need to get the official... for the sake of the problem, yes, maybe I need to tell them that it is. But for the sake of my count, did it for me, right? They both share those same ones. Now, that shows this is a rectangle. Square root of 34 means this is a rectangle. And by the way, we already know that this is a parallelogram. That's the first thing that they tell us. How about a rhombus? A rhombus, I mean, why do I say I know it's a square? Because it's a rectangle and a rhombus. What makes it a rhombus? The slopes. The slope of segment JL is negative 3/5. The slope of segment KM is positive 5/3. These are opposite reciprocal slopes. In a parallelogram, if the diagonals are perpendicular to each other, it is a rhombus. So rectangle and rhombus, I'll write it all, I'll type it all out. But this is a rectangle and a rhombus. If it's both a rectangle and a rhombus, then it is also a square. That is the final answer right there. Now I'll go faster on these other ones now that I've explained that whole thing. So hopefully you can be attuned with that. Because here's the thing, I am shortcutting from the textbook in that I'm using the visual. I mean, they're expecting you to use a graph, I assume. They're expecting you to use a graph, and I'm going to count off that graph. I absolutely will count off that graph. And the diagonals, listen, I'm going to give kudos to the textbook in one way. The diagonals are probably the better way to do it. There are other ways to check it, though. I could check the length of JM, ML, LK, and KJ, and, figure out if sides are congruent. It's a rhombus. I can figure out if these have opposite reciprocal slopes there. There's more than one way I could do that. I might test that for some of the problems because I know it's a parallelogram. So I'll show you some other ones. Number 56. Maybe I'll do it for like 57 and 58. Okay, maybe I'll do side lengths. I actually decided that that's fine. I can do that. All right, number 56. JKLM, we got negative 2, 7. 7, 2. Negative 2, negative 3. Negative 11, 2. Okay, that's a little off the map there. All right. Not very rectangular looking, I gotta admit. So also not very square looking. The question, the one in question is rhombus. Now, this is an easy problem. It's an easy problem because the diagonals are a horizontal line and a vertical line. Horizontal lines and vertical lines are perpendicular to each other. Also, I can count the distances here if I really wanted to show that it's not a rectangle. I don't want to say because it just looks like it when you might go, oh, hold on, it actually was. But this count right here from negative 11 to 7, that length is 18. And this length from 7 to negative 3, that length is 10. So not the same length there. This is a rhombus. It is not a rectangle, therefore it's not a square. We already know it's a parallelogram. That's the thing. We already know it's a parallelogram. We're just working off the perpendicular diagonal distances there. I guess all these, therefore, are the same length. Diagonals bisect their angles, yada, yada. I don't know if you know this. I'm recording. It's 4:41 in the morning right now when I'm recording. I started a little after 3 a.m., so on a Saturday. For anyone who cares, doesn't matter if you're watching this in the year 2036. That's what I'm doing. Why? I have no idea. Number 57. J. Now suddenly it's catching up to me. K. See, that's why they're showing X Games in the back. Is it still X Games? That's why they're... Oh, yeah. That's why they're showing the World of X Games in the background. They don't show that midday. L M. Okay. This is one of those things where they want to. I do not want to satisfy the book's wants. Answer the question for what it is, Mr. Robinson. What is this, everybody? We have vertical and horizontal lines. Those are by nature perpendicular. By nature, slope of 0, undefined slope. Perpendicular. It is a rectangle. The lengths can be counted. 1, 2, 3, 4, 5. 1, 2, 3, 4. Close, but not a rhombus. This parallelogram is a rectangle, and a rectangle alone. If it's not a rhombus, then it's not a square. So we went easy on that. Number 58. "588 problems, I have the right." 588 problems in the middle of the night. I have the right to make a problem as easy as represented. They gave it to us. They can't stop me from using that. So I don't think they can stop you either. J. K. Now, I'm still intent on doing what I want to do using the sides. I want to do it on this problem here. L. M. Looking like a rectangle. I'm looking like a rectangle. There are so many songs. I even wrote one once. I'm going to tell you stories. I'm doing this. I'll tell it in a bit. Okay, so with this one, looking rectangular. We'll see. Last time I talked about diagonals. This time I want to go on another front because I feel like the count can still apply to everything, knowing it's already parallelogram, right? I'm going to go from K to L in that rise-run thing, or this case a fall and run, and I'm going to do it from L to M. I think this applies just fine. From K to L, down 1, 2, 3, 4, 5, and right 1, 2, 3, 4, 5. From L to M is over 2 and up 2. Now, why can I use this? Because we know it's a parallelogram. We know in a rectangle, it's a parallelogram with right angles. We know in a rhombus, it's a parallelogram with congruent sides. Are these sides congruent? I don't mean visually. I mean numbers-wise. Are these sides congruent? No. 5 squared plus 5 squared is not going to give you the same thing as 2 squared plus 2 squared. And their square roots sure aren't going to be the same thing either. Not a rhombus. Is it a rectangle? Are there right angles? The slope of segment KL is -1. -5 over 5, which is -1. The slope of segment LM is up 2 over 2, which is +1. Those are opposite reciprocal slopes. Opposite reciprocal slopes. That makes a right angle here. And in a parallelogram, one right angle means all right angles. This is a rectangle. Clearly not a square, based on what we see here. But, so much was answered from this as well. So it depends on the property things you want to use. We know it's a parallelogram. So what's interesting about it, though, is how there's a reversal of roles from rectangle and rhombus. Excuse me. For all parallelograms, in a rectangle, the sides are perpendicular and the diagonals are congruent. And I don't know if I've ever said this statement out loud that I'm stating. In a parallelogram, like in my life, in a parallelogram, a rhombus's sides are congruent and their diagonals are perpendicular. They make right angles. So there's a reversal there. And so what I did as a test before here with diagonals was if perpendicular, it's a rhombus. Now I'm doing the sides if perpendicular, it's a rectangle. And before I would have said if diagonals are congruent, it's a rhombus. Now I'm saying if the diagonals are congruent, it's a rectangle. And then if the sides were congruent, it's a rhombus. So pretty interesting role reversal there. The tired wave is hitting me. Number 59. I think I'm more intent on wanting to do the sides when I can, now that I know that I can use that in that way, given it's a parallelogram. Number 59, J. K. L. M. Okay. Yeah, you know, once more, do I have to go off the diagonals for this stuff? No. I can... Oh, wait. This one's... Do I want to go off the diagonals for this one? Yeah. I didn't realize they were right above each other. Okay. We had a problem like this one before. Listen, visually, clearly not a rectangle, right? But we can also confirm it. We're going to ask ourselves, are the diagonals congruent for a rectangle? Otherwise, is it a rhombus? Now, is it a rhombus? Yes, based off the... See, this is when I want to use the diagonals. So diagonals, perpendicular. Diagonals not congruent. This length, 8. 7, 14 for that guy. Okay, so 8 and 14, not a rectangle, yes, a rhombus. Not a square, because not a rectangle. Okay, number 60. Number 60. We start at 5-2 again. J. And 2-5. Okay. Negative 1, 2. We haven't seen a square in a while. I'm guessing this will probably be a square. And M2, negative 1. Yeah, looking very squarish. Now, with this one, once again, I want to use the diagonals this time. So the only time that I actually didn't use the diagonals was, what, 58? I guess on 55, I could have also gone without the diagonals. But here, it's really nice, too. When points are above each other and, you know, this kind of stuff, you're getting back to this rhombus fashion because you know they're vertical and horizontal. So we know we're for sure a rhombus. Once again, I don't need to do anything to these slopes. I have vertical lines and horizontal lines. You gave me a graph. I can work off that. So I am a rhombus. However, the count is 1, 2, 3. And listen, I don't need to count the whole diagonal. Diagonals bisect each other. So 1, 2, 3, double that is 6. 1, 2, 3, double that is 6. KM is 6. JL is 6. That is true of rectangles. Congruent diagonals. That is a 4:50 a.m. alarm for me to wake up when I teach. It's a Saturday, so I don't need to do that. I don't need to say rectangle. It's just a rectangle. Rectangle and square. If there's any other proof that I'm in the middle of the night, besides skateboarding in the background or whatever's there, there's that. Square. Okay. All right. Remember, they are parallelograms. Let me yawn myself out. Give me a second. Okay, now I felt good overall with these, by the way. I was going to state that, you know, normally it's a lot earlier that we hit a bunch of word problems. We haven't seen any of those yet. We will. I know we ran into them, I think, in the example things, but now we're almost 3/4 of the way through, right? I haven't done them yet. Mathematical connections. In exercises 61 and 62, classify the quadrilateral, explain your reasoning, then find the values of x and y. Let me copy this thing over. Boom. So I was going to say that, you know, although there are 88 problems, it's not like number 34. Whoops. It's not like, hey, number 34, we start our mathematical connections word problems and proofs and stuff. I do know that we're going to have to do proofs later. I know because in the problem set, in the lecture portion, I think they said page 440, we prove those corollaries that a quadrilateral is. And I'm fine with those ones. They're not like these unique ones. Those are cool. All right, anyway, classify the quadrilateral, explain your reasoning, then find the values of x and y. Well, this is a rhombus. Now, notice they did say classify the quadrilateral. We don't know it's a parallelogram, but this goes right back to what I was just about to say about the proofs we have to do later. A quadrilateral with all congruent sides is a rhombus. Now, when they say classify it, they also want you to do the most specific one. They don't say rhombus and parallelogram and. It's a rhombus, and it's not a square. All sides congruent, but not right angles for a square. Okay? So we know it's a rhombus. They do say find out these things here. So let's find x. Now, if it's a rhombus, it is a parallelogram, and a parallelogram has consecutive angle supplementary. So x and 104 add to 180. So x is 76. Now, in a rhombus, all sides congruent, also as marked. 3y is y plus 8. Subtract y and divide by 4. So there's that, number 61. Number 62. Looking very squarish. I'm going to imagine it's a square. How would I explain your reasoning? Well, look at all the, not just look at that it looks like a square, it's the markings. All right, let's see. There's probably a little cutoff on my copy-paste job. Yeah, that's fine. Okay, number 62. Listen up, y'all. This is a square. How do I know it's a square? It is a rectangle. Let me just shrink this. Not that much. It is a rectangle because of the right angles. And a rectangle is a parallelogram. And this is a weird sentence. In a parallelogram with perpendicular diagonals is a rhombus. A rectangle and rhombus shape. A shape that is both a rectangle and a rhombus is a square. Now, there are probably more condensed ways to write that, but because I was typing, I was able to do that. That's what I would say out loud. So, again, here are the interconnections. The right angles make it a rectangle. Not all quadrilaterals can have a right angle, not all rhombuses, not all quadrilaterals with perpendicular diagonals are rhombuses, but because this rectangle is a parallelogram, all parallelograms with perpendicular diagonals are rhombuses. Now a square takes on all of that, so that's why I was saying this diagram looks very squarish by that nature, all the right angles. All right, let's find out x and y. Listen, on x, wait, do you have to find measures? No, just find the values of x and y. Listen, for x, I can go even easier than 5x equals 3x plus 18. I could say 5x is 45. Remember, in a square, these are all 45. Boom, 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 boom. These are all 45-degree angles. So x is 9. But if you want me to confirm that, let's go this way. 5x equals 3x plus 18. If they did the problem right, this should still be 9. Subtract 3x from both sides. Divide both sides by 2. So yes, no matter what you do, you still get 9. Or 3x plus 18 is 45, right? It's just 5x was easier to work off of. Now y, this is a length. This is not a measure, but it is a parallelogram. Diagonals bisect each other, so 2y equals 10 in this case. 2y and 10 are the same thing, so y is the cinco. The cinco of the cinco, and that is number 62. All right, number 63. I have no idea what's coming on this other side. We probably got to get into some of that. Some of the drawing conclusions and stuff. All right, so much for drill and kill problems, guys. Now we got to do this. Drawing conclusions. In the window, segment BD. See, okay, they have markings. They have right angle markings. I don't know if you can see them. They say the right angles. But segment BD, where's BD? Oh, BD is congruent to DF. Let's see what I can do here. I'm going to try and, because last time I did this, it did not look obvious what I was doing. So BD, you can see that, is congruent to segment DF. I'll mark those in a bit. And BH is congruent to HF. BH is congruent to HF. Also, we got right angles all throughout here. So let's do some of this. So boom, boom. Oh, hold on. BD is congruent to DF. Oh, yes, they're all congruent. They're all congruent. Got it. Rhombus. Also, they have right angle things here. Probably not so obvious here. And then move on, number 64? No. Part A, classify HBDF and AECG. Explain your reasoning. Okay, HBDF HBGF is right here. So it's a quadrilateral, four-sided shape, but it is a rhombus. Quadrilateral with all congruent sides. That's as much as we know about it. This is as little as we know about it. Now, there's a quadrilateral. AECG is a rectangle. Oh, ACEG. ACEG. I noticed when E wasn't next to A. ACEG is a rectangle. Probably should have typed this. Quadrilateral with all right angles. I think we're getting more into the corollaries. Numbers 61 and 62 really started that stuff. The corollaries of, they're not necessarily parallelograms anymore. You know what I mean? Now they're more of, are they what they are based off the minimalist definitions? If they just gave you perpendicular diagonals, for example, I wouldn't know it's a rhombus, because you can make perpendicular diagonals in non-parallelogram quadrilaterals and make it not be a rhombus. What can you conclude about the lengths of the diagonals AE and CG? Given that these diagonals intersect at J, what can you conclude about the lengths of AJ? Okay. I'll tell you what. This has nothing to do with a rhombus. AE and GC have to do with the rectangle. Remember, ACEG is a rectangle, and boom, boom, what I drew in green are diagonals for that. I'm going to type this one. Diagonals in a rectangle are congruent. So AE and equals GC. That's my conclusion, because diagonals of a rectangle are congruent. Given that they intersect at J, what you can conclude about the lengths of AJ, So AJ equals JE. These are the, like, bisected ones. JE, CJ, and JG, they're all the same. Because a rectangle, or parallelogram, whatever, a rectangle's diagonals bisect each other. Now, this kind of has to do with the rhombus. Given that they all intersect at J, J is on HD. HD are parts of the... J is on HD. HD are parts of the... it's part of the rhombus's diagonal. And J is a midpoint of each diagonal because it is on the rhombus's diagonal. Which has points on the rectangle. So the rhombuses is made within the rectangle, and then et cetera, et cetera, et cetera. I'm not going to do like a triangle congruence proof on that. It's just more that when J's on that point, then we know that that's the midpoint, which means that it's the bisected part, which means. So all those parts are equal there. Okay, number 64, abstract reasoning. Order the terms in a diagram. Hold on, 64. Order the terms in a diagram so each term builds off the previous terms. Explain why each figure is in the location you chose. Order the terms in a diagram so each term builds off the previous terms. Okay, so here's what I would do here. I have quadrilateral as like the head of something. Now, here's the thing. We're not in section 6.5. This would have been a better thing for section 7.5 when you learn trapezoids and kites. Because there are other things that you can spur off of. So a quadrilateral can more uniquely become a parallelogram. Now, not all quadrilaterals are parallelograms, but all parallelograms are quadrilaterals. All these four-sided shapes are quadrilaterals. So this happens when you have two pairs of opposite parallel sides. Two pairs of parallel sides. That gives you a parallelogram. This kind of diagram thing is going to be very important for what you do here. Like I said, with trapezoids and kites, it would also be very important. Parallelogram can kind of go into one of two forms hereafter. Keep in mind, this diagram is kind of trickling down. A parallelogram is everything a quadrilateral gives. So quadrilateral gives you things, and boom, I have a parallelogram, 2 pairs of parallel sides. From a parallelogram, I can now spur off and either become a rectangle or a rhombus. What makes a rectangle or a rhombus? Well, either a parallelogram or quadrilateral, technically, with all right angles. Each term builds off the previous terms. I'm trying to think if I want to do even more so on the like congruent diagonals thing. I could. I'll stick with this for now because I could have done quadrilateral to rectangle. I'm wondering if I should. Ooh, I'm wondering if I should do that. Maybe should I do that where it builds off of it? Let me think if, because here if I have, I've never done diagrams that way, so I probably won't. I was thinking here I could say a quadrilateral with all right angles is a rectangle, but let's just say they do say builds off the previous term or terms, as in, boom, I'm going to do that. So anyway, all right angles in a rectangle, a rhombus is all congruent sides. Now keep in mind, because here's what I was going to do. I was going to do quadrilateral, boom, all right angles, quadrilateral, boom, all congruent sides. That would have worked. In the parallelogram, I would have said, oh, congruent diagonals, perpendicular diagonals, angles by diagonals bisecting angles. You could have done that, but I'll leave that. And then anyway, the square is any version of a rectangle and rhombus. So if a rectangle becomes a rhombus, it's a square. Therefore, if I get all congruent sides of a rectangle, I'll have a square. And if I get all right angles of a rhombus, I'll get a square. So I'm kind of going that way with it. If they do this in section 7.5, they'll give the quadrilateral into two other forms with trapezoid and kite. 2 pairs of parallel sides, 1 pair of parallel sides, no pairs of parallel sides, and then you can kind of do things off that, which is nice. So that's my explanation on how I trickled that thing down. So all of those can trickle up and be inherited that way. All right, 65 to 70. Hopefully these are kind of, they do say explain your reasoning, but hopefully these are kind of quicker ones based off what we can do. I want to try and type these ones because that seemed to work pretty well. And I want to try and do that more often when it's ones like this. So 65, because then I'll write out the sentence. A square is blank or rhombus. Okay, these are great kinds of questions. Always, sometimes, never. Oh, number 64 is going to be really good for this. Okay, before I go through, at least for the first 2 questions, a square is always a rhombus. If it's a square, then it's boom, boom, boom. If it's a square, then it's boom, boom, boom. It's anything before it. If it's a rectangle, it's boom, boom. If it's a rhombus, it's boom, boom. If it's a parallelogram, it's boom. Remember, a quadrilateral can be a square, but a square must be a quadrilateral. Okay, it's that thing. This is what can be. This is what must be. So when they say this in always, sometimes, never case, a square is always a rhombus, but a rhombus ain't always a square. I don't know how I want to explain that thing other than I want to go based off of my thing from above. Just say, look at the diagram. But a square is always a rhombus because a square always has congruent sides. Right? So that's kind of how I want to work out that. All right, number 66. So the explain your reasoning, I might not be very good at saying what you want to put, but I'll try. A rectangle is always, is sometimes a square. Sometimes a square. So a square is always a rectangle. Oh my gosh. A square is always a rectangle, right? But a rectangle is sometimes a square. It could be. It's possible. What would make it one? What wouldn't make it one? If it had all congruent sides, then it would be a square. If it doesn't, then it's just a rectangle. There's nothing wrong about just being a rectangle. I was once a rectangle. It's okay. Then I got congruent sides. All right, a rectangle always, sometimes, or never has congruent diagonals. A rectangle always has congruent diagonals. That is one of its theorems. theorem is all I'm going to say there. I kind of want to italicize the reasons, so it kind of like that. This is my reason. All right, number 68. The diagonals of a square blank bisect their angles. Well, I know the answer. I just want to get to there. The diagonals of a square, they always bisect their angles. Whoops, underline. It's angles. Okay. Yes, always. Also true of rhombuses, which a square is, as we showed in number 65. A square is always a rhombus. Number 69, two more. A rhombus blank has four congruent angles. So this is kind of like, hold on. What? I don't know why it's doing that thing. Sometimes. Like that. Like, what's that? Has four congruent angles. So this is kind of like the rectangle one from 66, only it's not bringing up the shape portion. So like this would be if 66 said a rectangle always has four congruent sides, but it said rectangle square. I said if it has four congruent sides. Now I'll say a rectangle sometimes has four congruent sides if it is also a rectangle. So if it is also a rectangle, then that would be true. And again, I don't know what's going on with this typing thing. Sorry about that. And then number 70, I think my thing is information overload. By the way, I didn't think about it until this very second. I'm going to freak out if it ever happens. I did note that I once had a blue screen of death crash when I was recording a video. Thankfully, that was 40 minutes in, but I still haven't recorded that video again. I don't know when I will, but I am 2 hours in right now. If I get a blue screen of death, guys, you won't know about me talking about this, but I'm not going to redo this recording. There are things I'm going to forego because my life matters more to me. My sleep matters more to me. A rectangle blank has perpendicular diagonals. Okay, so a rectangle is congruent diagonals, but when they're perpendicular, you're making a square, right? A rectangle sometimes, by the way, were there any nevers? I'm going to double check and make sure there weren't supposed to be any nevers. But a rectangle sometimes has perpendicular diagonals. When it becomes a square, which means when it's also a rhombus, right? So, you know, so this is only true when a rectangle is a square, because also true of rhombuses. I kind of said that once before in kind of the thing, because that's when that would happen. Okay, were there any, I really wanted a never. Let's see that. A square is always a rhombus. Yes. Oh, a square is always a rhombus. A rectangle, sometimes a square. Rectangle always has congruent diagonals. A square always bisect their angles. A rhombus sometimes has four congruent angles, and then a rectangle sometimes, yeah. So no nevers in that one. It's too bad. I kind of want a never in that case to really hit home what doesn't work for some of the quadrilaterals. Okay, that was probably the last of my fast problems. Using tools, proving a theorem. Let's get some things out of the way. You want to mark off a square region for a garden at school. You use a tape measure to mark off a quadrilateral on the ground. Each side of the quadrilateral is 2.5 meters long. Explain how you can use the tape measure to make sure the quadrilateral is a square. Okay. Use a tape measure to mark off quadrilateral on the ground. Each side of the quad is 2.5. Okay, so basically when we did the 2.5 meters part, you've assured that you've made a rhombus. Now you have to do something to also make sure this quadrilateral is a square. You have a lot of options, but now that you have a rhombus, you'd want to now make sure that either your diagonals are congruent, or you want to make sure that you get a right angle on one of the things. So you have options here. You just want to make sure that also gets a rectangle property. That's all. So the 2.5 meter sides assures a rhombus. To make sure the quadrilateral is a square, you have one of two things. Either make opposite points, let's see, mark quadrilateral, either make sure you have a right angle from two of your sides, because then all of them will be, or make sure the diagonals are congruent, equidistant, are congruent. Either of those, as a rectangle, would have. If your rhombus is a rectangle, you'll have a square, and that's kind of what you want to build off of. That's the idea. All right, number 72. Proving a theorem. Use the plan for proof below to write a paragraph proof for one of the rhombus diagonals theorem. I'll probably mark things up on this one. Oh, they have a plan for proof. Wait. Then why don't I... Oh, okay, I see. They give you the plan. I'll probably mark this thing up as I go. So given it's a parallelogram, prove it's a rhombus. Okay, so plan for proof. I don't really need the plan, but for plan for proof, I'll use their one and then go off that. They're giving you everything. I think they just don't give you the reasons. Okay. A, B, C, D, given it's a parallelogram and you got a perpendicular thing, prove it's a rhombus. Remember, we learned that these are true, but you got to do this for yourself now as a proof, or I got to do it for you. Because ABCD is a parallelogram, its diagonals bisect each other at X. So that's something we'll state. So diagonals bisect each other, so we can state congruence here. Okay? We're going to do some sort of thing where something's congruent to something else. They're giving us the plan. Use the fact that these are perpendicular to show that two triangles are congruent. BXC, they're going to go for BXC and DXC, two of them that are right next to each other. Use the properties of a parallelogram to show that it's then show that BC is congruent, boop, 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 to DC like that. Use properties of parallelogram to show it's a rhombus. So that idea, we're then going to build off opposite sides congruent and those things congruent to each other, transitive property, all that kind of stuff. So, okay, here we go. I guess they didn't give us everything. So because it's a parallelogram, diagonals bisect each other. Okay, so no problem. Is I'm going to type it, and anytime something's congruent, I'm not going to be able to have congruent yet. I'm going to say equals, and then I'm going to put congruent symbols above it. I'll say it out loud, though. So ABCD is a parallelogram. That is a given. So because diagonals bisect each other in parallelograms, then BD... So here's the thing. I don't care about AC. I don't care about AX congruent to AC. I'm only going to use BX congruent to DX. Now remember, I'll do the congruent things later, but BX is congruent to DX. The right angles, because AC is perpendicular, I'll just put that for now. Perpendicular to BD. I'll do the whole thing in a bit. Actually, can I just use the underline? Can I underline it? Sort of. There we go. Because perpendicular to BD. Angle DXC and angle B. I'm really going to go paragraph proof instead of two-column proof thing here. I'm going to kind of type these all as one. Are right angles and therefore are congruent. In one sentence, I did probably 2 or 3 steps of a two-column proof right there. Okay, and therefore are congruent to each other. Knowing they're congruent is going to be important for what I say. XC is congruent to itself by the reflexive property. So here's what we really have, because I know I drew some things up before for the plan. Right now what we have is this, because I want to tell you why these triangles are congruent. These angles, they're not only right angles, but they're congruent to each other. More important to state they're congruent to each other. And this thing's congruent to itself. I got a side angle side case with side angle side right there. These two triangles are congruent to each other. Let me do some markings now that I'll keep typing, but I'm going to give you that, and that, and that. Okay. Therefore, triangle, I'll put triangle symbols in a bit, BXC is congruent to triangle DXC by side angle side congruence theorem. And CD is congruent to CB by CPCTC. Corresponding parts of congruent triangles are congruent. So let me mark some things up, and then I'll go back to tell you the rest of my plan. So triangle this is congruent to triangle that by that, and these are congruent to each other by CPCTC. Okay, so now, this is kind of in green. These are congruent to each other here. Okay, so here's what we're going to do next. Opposite sides of a parallelogram are congruent, okay? Opposite sides of a parallelogram are congruent. That's the theorem. I know I'm not saying the theorem, but are congruent. So BC is congruent to AD, and CD is congruent to AB. So here, what I'm going to now mark up is these are congruent to each other, AB and DC, and then AD is congruent to BC. Now you can see they all have three congruent tick mark things for, you know, the way that kind of works itself out. That's the transitive property. They're all going to be congruent to each other. I don't know if I can mark it and say that they're all congruent, but, you know, AB is congruent to BC is congruent to CD is congruent to DA, or AD. I want to do alphabetical. By the transitive property of equality, of congruence. ABCD is a rhombus by definition. I want to say by definition. By definition, ABCD is a rhombus. Our rhombus. Okay. So that would be the proof of that one. I almost now feel like a two-column proof would have been faster. Because I got to do all that. Okay. There we go. So we had to prove all sides were congruent, basically. Right? We had to get to the definition. We can't say, oh, diagonals bisect their angles and things like that. No, no, no. That's not stuff that we know at that stage. We're proving that this is enough information to show the diagonal theorem works. Right? Anyway. Okay. 73, 74. Write a proof for the part of the rhombus opposite angles theorem. I wonder if there's enough for me to copy paste that. I don't think so. This is a way different setup. I'm probably going to use a two-column proof then. So we have the givens we're going to prove. I'll just leave that stuff the way it is, and I'll mark it up over there by working stuff out over here. I might turn on my heater. Let me turn on my heater. It's cold. Okay, pardon the hum of a heater if you hear it. All right, let's go. Statements. Reasons. Okay, I'll try and mark up what's on that side. All right, we have several givens here. So, PQRS is a parallelogram. Okay, given that it's a parallelogram, y'all, well, I don't know what my plan for the proof is, but given that it's a parallelogram, we can use opposite sides parallel, we can use opposite angles congruent, we can use opposite sides congruent, a lot of stuff now that we know parallelogram. Let me start planning out a proof because they have the bisectors, therefore we're going to say that angles are congruent. I can do the diagonals bisect each other. I can do this part of a parallelogram. I'm going to have a lot for a case of prove it's a rhombus. Yeah, I can do a lot for triangle congruence here. I can use angle, side, angle. I can use side. I can use angle, angle, side. So I'm going to work off of the, let's see, I also have to figure out which triangles on proof congruent here, because if I do, I can use opposite sides congruent by definition of parallelogram. I can do angle, side, angle with these two sets. And then proving it's a rhombus. I want to prove that all of these... Oh, I want to prove all of these are congruent to each other. Am I allowed to do that? All four at the same time? Sorry, I'm thinking out loud on this thing here. I can use reflexive property. I can use diagonals bisect each other. Let's do the inner workings of two sets of triangles. Okay, I'll do the inner working of two sets of triangles. So I'll do this and diagonals. Listen, I'll just use this. I don't even know. I don't even need to use the parallelogram part till the very end. I'm going to do the same thing that I did before and use the transitive property at the very end once I prove a set of sides congruent. I'm pocketing this part for the end. I'm going to start with the diagonal parts. I'm going to say, and there are a lot of ways to do this. It's just, I almost have, it's like a good problem to have, but I have so many ways to go about it. I didn't want to know what was best. And I don't know if this is best, but bisector, sorry about that. You know what it says. That's given. And SQ. Actually, before I do the SQ one, let's just say based off that bisector, segment PR bisects angle SPQ and QRS. Therefore, we can name those things congruent by definition of bisector. So I'm going to say angle QPT is congruent. This is the part that takes a while. QPT is congruent to angle SPT. And angle QRT is congruent to angle SRT. That's definition of angle bisector. See, they may have marked it on the thing. They shouldn't have. They should have just given us that. And then we can work off that. So now, probably faster to copy and paste some of this stuff and rewrite them, but sometimes it gets a little weird. So on 4, same thing. SQ now bisects the other angles. Angle PSR and angle RQP. That was the given. So statement 5, angle, so now I'm talking about these two angles being bisected. So now these bits are congruent here. And they're congruent to each other. See, the markings of them being congruent to each other lends me to believe that I want to bring something up with that. Still wondering if I should. I don't think so. All right, angle PQT. After this, I'm going to fill my water bottle. Angle PQT is congruent to angle RQT. And angle PST is congruent to angle RST. Definition of angle bisector. Okay, this is just from given stuff. All right, I'm going to build pretty small here. I'm going to say QT is congruent to itself. Now, I'll be honest, I'm probably not doing it the way that angle QT. Segment QT is congruent to itself. I'm probably not doing it the way they'd want me to with regard to all these things being congruent. There are probably ways I can prove two bigger triangles congruent with that sets of the bisectors. But I can't use angle. Dude, there are a lot of ways I could have done this. I could also say, I could forego what I'm saying there and talk about these bigger triangles and say this is congruent to itself by reflexive property. I got an angle side angle with that guy. And then I can use the opposite things. Oh man, I have some options here. But I'm just gonna go off this one. There's so many ways, guys. Mine is not one way. There's so many ways. But QT is congruent to itself by the reflexive property. Therefore, I got those two top triangles. hold on. My mouth's drying. I'm gonna get water. Okay. I don't know where I was. QT congruent. Okay, so what I'm thinking of doing, I'm wondering if I can get all triangles congruent at the same time. Probably, again, so many ways to do the problem. When I say QT is congruent to itself, I can now say that this triangle is congruent to this one by angle side, and I'll do that. But then I'm going to say TS is congruent to itself, and then boom by angle side as well. I mean, it's all there. It's all set up with what's marked as congruent. Right? Let me actually go back. I said PQT is congruent to RQT. Where is PQT? PQT in okay, yes, I can do that. But now this is in its own ooh, that's in its... Boy, I have to make sure that, because the markings are there, but I can't treat this as congruent to this, because I never said that those were congruent to each other. I can with properties of a parallelogram. PQRS is a parallelogram. I can say how opposite angles are congruent. This is just hard to do in a 2-column proof because I don't want to do all these things of measures of, equal and stuff. When I see them, I think I'm good with it. Let's see. I might... Oh, boy. Now I'm suddenly in a quandary. Let's go with... Let's switch this QT. I'll save the reflexive property thing for a moment. Let's go with the parallelogram part. I'm going to say angle, the big angle Q, angle PQR is congruent to angle PSR by parallelogram opposite angles theorem. I forget suddenly why I was saying that. I don't know if I need that information. I forget why I suddenly wanted to say that. I forgot why I wanted to say that. I'm going to say this triangle is congruent to this one. I don't think I needed to say what I was going to say there. This is congruent to that. This is congruent to that. I don't know. This proof has so many different like no pun intended, has so many different angles that I'm wondering what I want to do with it. Basically, I need a CPCTC thing, right? If I say this triangle is congruent to this one, then I can say, however I name the triangle, then I can say that this is congruent to that, and that's congruent to that by CPCTC. And then I can say opposite sides of a parallelogram are congruent. I guess I don't need that. Okay, I don't need what I just said here. I don't know why I thought I was going to put that. I don't know. I don't know how I was going to say that. Okay, let's say PR is congruent to itself. This exists in both triangles. PR is congruent to itself by reflexive property. Sorry, this is just one of those things where I want to plan it with you. This is the conversation and the dialogue that I have with you guys on here. All right, so that congruent to itself, just a little marking there. And so now those two triangles are congruent. I can say triangle PQR is congruent to triangle PSR by, that would be angle side angle. And now using CPCTC, so I said this triangle congruent to this triangle. So by CPCTC, PQ is congruent to PS and RQ is congruent to RS. I wonder how the book would have done this. PQ congruent to PS and RQ congruent to RS by CPCTC. Whew. Now the parallelogram part. Step 1, PQRS is a parallelogram. Now I can say that PQ is also congruent to RS. And so these are opposite sides. PQ congruent to RS. Now I can like double mark that. And then RQ congruent to PS. Or PS congruent to RQ. I don't know if I have to say a transitive property thing after this, that they all are. I probably do. So, parallelogram opposite sides theorem. Yeah, I don't know. Sorry. I didn't need both sets of diagonals to be bisected, basically. In fact, when it's a parallelogram, bisecting the angles. I don't think I needed both sets of angles to be bisected. I think I only needed one set to bisect the other. Something. I don't know. All right, so 10, now I have PQ congruent to, I mean, they're all congruent to each other now. I'm just going to ensure it and say PQ congruent to RQ and RS congruent to PS. All the same. I don't know if that statement's needed, but transitive property of congruence. All the same. So PQRS is a rhombus. I'm very cold. PQRS is a rhombus by its definition. And I have a another proof below. I kind of want to see, where's my circle thing? I kind of want to see all that I have to prove here. It's 73 and 74 that we're doing it for. All right, that was 73. Let's go to 74 and see that I can do you one better with a plan. See, maybe I should use their plans. Given WXYZ is a rhombus, prove now that the angles are bisected. Okay, so that the statements. Now they start us off. They say is a rhombus. All right, so first given. All right, so they give you some markings of what things are congruent. I'm just going to mark them all congruent at the same time right now. WX, XY, YZ, and WZ. I can use any of these off that after. Even if I want to do WZ. Definition of rhombus. Okay. Now, I'm proving that the angles get bisected. Those ones specifically. I don't know if I can use everything else about a rhombus around there other than what's true about it with a parallelogram. Excuse me. So if it's a rhombus, then everything from what we know about a parallelogram is true. So prove that things are bisected. We got to prove little mini triangles for both of these are congruent. I don't know if we got to do one at a time. So I got to prove like this triangle is congruent to this triangle, for example. Is congruent. Listen, just prove all four triangles are congruent at the same time. So here's what we'll do. We got to prove all four are congruent. We have markings here. I'm just trying to decide if we can do the, yeah, we're just going to do a side one. So diagonals bisect each other now as well. All right, so they're not all congruent. They bisect each other. So WV is congruent to, I don't know if I have to say it's a parallelogram because a parallelogram is a rhombus, but I'm just going to say that diagonals bisect each other. YV, because it's true of a not because it's true of a rhombus, because it's true of a parallelogram. And then ZV is congruent to XV. Parallelogram. Bisector theorem? Diagonal bisector theorem. So this is These two congruent. Oh, I was going to say something before about, so I made a, I was going to say something about a song thing. This was a long time ago. I think when we were graphing rectangles, and I said something about the diagonals. I forget what song it was. I'll have to play it back. But I once wrote a song for a student who was trying to do a project. I was subbing a class, and they're like, for my calc class, we have to make a song. And together we came up with this calculus song for a parody for Rewrite the Stars, the Greatest Showman thing. And every so often I'll come up with a song or a song idea, a concept, like a parody, for a topic. And I've never actually made one. I never actually recorded one. All right, anyway. So here's the thing. All these triangles are congruent by side, side, side. We're going straight into this. Triangle, they're all going to be together as one. Triangle W, I have to find parts that correspond though. WVZ, I'm going across the 3 and then the 2, is congruent to triangle WVX, is congruent to triangle YVX, is congruent to triangle YVZ. By side, side, side. See, this is the kind of thing that I wasn't doing on the last problem that I wanted to do here, where it's merging everything, it's taking everything in as one. This is probably how the last problem would have been done. Now, we got to say that there are bisectors involved based on parts that correspond. The W's correspond, see the ones correspond together. W with Y with Y. WV, WV, YV, YV. 1, 2, 3, 1, 2, 3, 1, 2, 3. So you got to find what parts correspond here, basically, and show what parts can then be congruent. I'm allowed to say now that angle, see, it's all about the bisectors. I'm now going to say that this angle is congruent to this one and this one and this one. Why can I say those are all congruent? Because look at how I'm going to call this. I'm going to call angle VWZ, VWZ. Maybe I should have called the triangles by the V's to start with. But VWZ is 2, 1, 3. I'm going to say it's congruent now to 2, 1, 3, VWX, and VYX. Yes, I can do this. VWZ is congruent to VWX. Yeah, I really should start from V with all these. VYX and VYZ by CPCTC. Because those parts correspond and are congruent, that means that WY bisects those angles by definition of angle bisector. Bisects angle ZWX and angle XYZ by definition of bisector. And then it's going to be the same for all the other ones. It's just going to be a lot to write. So 7. Now I'm going to say that these ones, I have the heater on it. I'm just freezing. I can put on a sweatshirt, but tough it out for now. Maybe I should close my door. Angle VZW, so it's the same, just I gotta find the letters. Angle VZW congruent to angle VZY. It's just more corresponding parts. Angle VXW and VXY. CPCTC. And then therefore ZX bisects these two angles. Angle WZY. I know my handwriting is tough on these. And YXW. Part of it is the technology stuff I'm using. Definition of bisector. Part of it is I've been working for over 2 hours since the middle of the night. All right. Numbers, okay, no proofs here. So number 70, and I know I have to do the proofs of the corollaries later. 75, abstract reasoning. Will a diagonal of a square ever just divide the square into two equilateral triangles? Explain your reasoning. Okay, quick answer. No. No, because equilateral triangles have 60-degree angles. And diagonals of a square will make 45, 45, 90-degree triangles in any which way, whether you're talking about just a square. So whether it's a single diagonal, it says will a diagonal, oh, it says will one diagonal, but whether it is this is a 45, 45, 90, or even with two of them, this is a 45, 45, 90. You'll never make equilateral triangles out of those. If only the proofs were that fast. Number 76. Will a diagonal of a rhombus ever divide the rhombus into two equilateral triangles? Explain your reasoning. Also, no. 76. Well, let me make sure. Let me make sure that that's not untrue. Also, no. A single diagonal, not two diagonals. I take it back. That's probably yes. That can be true. So, yes. If I'm gonna draw it. I'm not gonna write it. My explanation. If you have 60-degree angles to start with here, so and the 60 is not the one that's cut in half. So if this is 60, then these two would be 120, and then that gets bisected. So this gets, because diagonals are bisected there, so now suddenly that's 60 and 60 and like that. Clearly I didn't make this like to scale or whatever. So if angles are 60 and 120, angles are 60 and 120, and 120 is bisected. I thought they were saying if two diagonals were drawn, and 120 is bisected. Now, it's going to be bisected. It's a rhombus. It's going to be bisected. I just mean that you do that one instead of the 60-degree one. All right, 77, critical thinking. Which quadrilateral could be called a regular quadrilateral? Explain your reasoning. So if you know regular polygons, we're talking about ones that are equilateral and equiangular. So the square. A square, my pen is in the way. A square is a regular quadrilateral. I'm going to quote it. Regular quadrilateral. Because regular polygons are equilateral and equiangular, which a square also is, as it's both a rectangle and rhombus. Or rhombus and rectangle. Okay, number 78. How do you see it? What other information do you need to determine whether the figure is a rectangle? So we have a single right angle. Okay. Now, they're asking for one bit of info. It sounds like they want one bit of information. You know, it's not just like, well, if I knew they were all right angles, or well, something like that. So, I'm freezing. I'm gonna put on a sweatshirt. Okay, so I went for a jacket. Okay, and I closed my door. Okay, what other information do you need to determine whether the figure's a rectangle? So again, you can't just say like, well, if I got, you know, this, and then it's good. They want to hear one thing. Some of these things wouldn't work out the way you'd want them to. Like, if I had congruent diagonals, this wouldn't be enough because I could do something where it's like, diagonals are totally congruent here, but this is the right angle. Like, I don't know. There are ways that you can offset that. I can make that a right angle, but then that doesn't mean that this is a rectangle. You know, things like that. Anyway, one piece of information, we've done this a lot already when we were doing earlier on about just parallelograms, and like we have a single right angle, then it was a rectangle. If I knew this was a parallelogram, that would be cool. That would be enough. What other information? If I knew this was a parallelogram. If it is a parallelogram. Now, that means a lot of things. Right now, just opposite sides parallel. But if it's a parallelogram, that would be enough. And then I'm good. Like, if I was told. All right, number 79, reasoning. Are all rhombuses similar? Are all squares similar? Explain your reasoning. It's funny, the very moment I put my jacket on, now I sink. Maybe there's a certain level of weight on me now that makes my chair sink, because I wasn't actually sinking for a long while there. Anyway, are all rhombuses similar, all squares similar? Explain your reasoning. Okay, similarity means they grow in proportion with each other, that they keep all their angles the same, that they maintain their angle basis while they do this. Rhombuses are not all similar. Rhombuses can change their angles by nature. Not all rhombuses are similar. Now, that doesn't mean that all rectangles are similar, by the way. Rhombuses are similar. I wish they asked about rectangles, as their angle measures can change. All squares are similar, however, because their angles remain the same and their sides remain in proportion with each other. Something that a rectangle does not need to guarantee either. Yeah, now I feel myself sinking again suddenly all these times. So I think the jacket just put on that little extra weight that makes me sink. I was wondering why I wasn't sinking, and I didn't want to jinx it, but now I actually am. Okay, number 80. Those go pretty fast outside any proofs that are coming up. Use the rhombus diagonals theorem to explain why every rhombus has at least 2 lines of symmetry. So, 80. So this is why it's better to draw the rhombuses in that kind of like diamond way. Let me try and make one like that first and then go off of that here. I got to kind of turn my head and go. That's good enough for now. Let's see if I can get to that to this state. Yeah, it's pretty good. Okay, so let me do it the other way, though. I get kind of thrown off by the box thing. Okay, so boom, boom. It's almost like a 2-column proof in a way of what I want to talk about here. Did I actually lock that? Sorry, let me construct this first, then I'll talk. I want to think about how I'm allowed to say the answer to this question. But the diagonals are the lines of symmetry is the one thing I first want to kind of mention here. Whatever. It's probably not perfectly to scale. Just kind of pretend like I got that right. Okay, so here's my rhombus, and then I have my diagonals, right? Now they have 2 lines of symmetry. Here's one line of symmetry, which means that this is a reflection of this. And then here's another line of symmetry, which means this is a reflection of that. They flip over those lines. Use the theorem to explain why every rhombus has at least 2 lines of symmetry, because it bisects the diagonals. So this is congruent to that, this is congruent to that, and it creates that aspect of symmetry there because of the bisecting part. And of course, the diagonals bisect each other as well. The diagonals theorem is just for this, and then this bisects this as well in that kind of way. It's this whole, I can use the side angle side word congruence thing. All these things are congruent in these own respective ways, and then these are congruent here, and these are congruent here, and rhombuses are congruent there. The diagonals theorem, this is everything about a rhombus you ever need to know. It's pretty freaky looking drawing now. But it's these parts right here. The congruent angles, and then the congruent angles on these sides here, based on them bisecting each other here and there. Mostly just because the rhombus's diagonals bisect their angles. The diagonals bisect their angles. And then everything about a parallelogram that you need to know. But that's really just the big thing that I would go off of. I can't really think of more that I'd want to say on the matter. But yeah. Anyway, I don't know if I'm saying that beautifully, but all that stuff creates so much symmetry all throughout. And then, again, they bisect each other, they're perpendicular to each other, all that stuff. All right, 81. Write a corollary as a conditional statement and its converse, then explain why each statement is true. So keep in mind all of these. I did say this in the lecture. I did say this in the lecture portion. Or at least I stated about the biconditionality of it. So the initial corollaries are the if and only ifs for quadrilaterals. So let's see if I remember how to say them. So the rhombus corollary is a quadrilateral is a rhombus if and only if all sides are congruent. So now a quadrilateral is a rhombus if all sides are congruent, is now going to be kind of the, let me first say rhombus corollary. Rhombus corollary. So the first one is this guy. Now, if I flip it, I'm going to state its converse. A quadrilateral has all congruent sides if it is a rhombus. Okay, so let's try and, we wrote as a conditional and its converse, explain why each statement is true. Why is this true? That's a good question. Like, I want to try and say why it's true without doing a whole paragraph proof or 2-column proof or something. It's a rhombus if all sides are congruent. If you have all sides congruent, well, it's a 2-column proof thing. I don't know how I want to state it beyond the whole, because I don't want to do massive 2-column proofs for these things, if that makes sense, because that's where I would go off these. I mean, the original is the rhombus's definition. I don't want to do 2-column proof with this. Because of its definition. Like, yeah, right? Now this one, a quadrilateral, if I'm kind of saying that thing right, to say that, you know, if it has 4 congruent sides, then it's a rhombus, you can do, well, you can say this. You can say the parallelogram, right? Parallelogram has opposite sides that are congruent. A parallelogram has opposite congruent sides already. And a parallelogram with 4 congruent sides is a rhombus. That's kind of where I want to go with it. Yeah, because, wait. Oh, this isn't, wait, a quadrilateral. Oh, yes, if it is a rhombus. Hold on. Do I want to say if and then? Hold on. I want to do this again. Quadrilateral is a rhombus if it has all congruent sides. This is fine, but they said a conditional statement, so I want to do if then. So let me do this again. I was trying to do the quadrilateral. I was trying to do the corollary with the if and only if. So I want to say if a quadrilateral is a rhombus. A quadrilateral is a rhombus. Then it has all congruent sides. I'm going to say 4 congruent sides, because of its definition. And then if a quadrilateral has 4 congruent sides, then it's a rhombus, because it's conditional. A quadrilateral has 4 congruent sides, then it is a rhombus. Because I was looking at my conclusion here. Looking at my conclusion going like, well, I'm not really saying my conclusion as it being a rhombus there. All right, I think that's going to help with some of the other ones that I say after that. All right, so number 82. Let's do the corollary for, I lost my thing. Move, page. All right, let's do the corollary for rectangle. I was going to copy paste, but I don't think it's going to work very well. All right, rectangle corollary. All right, so what is its corollary? I don't remember. Rectangle, all right angles and stuff like that, right? So now I want to say if a quadrilateral is a rectangle, then it has 4 right angles. Okay, now, that would be the definition of a rectangle. True by the definition of a rectangle. So that's the original. Now the converse would be if a quadrilateral has 4 right angles, then it is a rectangle. Now this would just kind of be the same thing with talking about a parallelogram, right? the parallelograms opposite angles are congruent. A parallelogram, a quadrilateral 4 right angles. The 4 right angles mean it's a parallelogram because, okay, this has a so it's the converse. Sorry, I'm trying to think how I want to say it. 4 right angles. So a quadrilateral. There we go. A quadrilateral with 4 right, with opposite 4 right angles means it has congruent opposite angles, which a parallelogram also has by the converse. A parallelogram with any right angles is a rectangle. That's where I'm going with that. Okay. Kind of hard to say what I want to say. I'm supposed to be good at that. All right, 83. Square corollary. Almost done, I hope. I thought we were supposed to prove the corollaries. Maybe that's still coming up. Because, see, that's when they're having me do these things, I'm like, do I have to prove it? And, like, I'm going to prove them later, I think. Square corollary. Because then I can do the triangle things. Not very fun. If a quadrilateral is a square, then it has 2 things. 4 congruent sides and 4 right angles. Then it has, well, I don't say that. I can just say then it's a rhombus and a square. I think that's what it actually says. Then it is a rhombus and a square. And a rectangle, I should say, rather. Okay. Now, if a quadrilateral is a rhombus and a rectangle, then it's a square. Okay, why? Why? So this is one. The first one, once again, is just it's just the definition of a square. But it's really, they're asking us how to state the other one's true, really, right? So this one has a few things that we can talk about here, right? If it's a rhombus, I mean, I can go off of the, I'm less about the parallelogram this time, because now I'm just get to talk about rhombus and rectangle with it. So let's just kind of do one thing at a time with that one. So we can then say, if so it's 4 congruent sides, right? If it's a rhombus, then it has 4 congruent sides. It has 4 congruent sides and 4 right angles. I think I can just go off that. Let's see. There's 4 congruent sides and 4 right angles by definition. If it's a rhombus and a rectangle. And a rhombus with right angles is a square, or a rectangle with 4 right angles. With 4 congruent sides is a square. I'm not great about explanations, y'all. I can verbally explain it better than I can type them out, but I'm just not great with them in general. All right, 5 more. Making an argument. Your friend claims a rhombus will never have congruent diagonals because it would have to be a rectangle. Is your friend correct? Explain your reasoning. Well, a rhombus can be a rectangle, in which case it's also called a square. So a rhombus will never have congruent diagonals. So 84. Your friend's correct and incorrect. Their conclusion's incorrect. The rhombus, a rhombus, your friend is incorrect in that it can have congruent diagonals. Yes, it would then be a rectangle as well, which means it would also be a square. But that does not negate the fact that it is still a rhombus. feel a lot warmer. I think, I don't know if the jacket's helping more or the jacket's a temporary one. The heater is better now that my door's closed. But now my chair sinks a little bit. Yeah, your friend was right and wrong. It's like, well, hold on a second. You're leading into the wrong argument for your conclusion. All right, 86, 87. All right, everything else is a proof here on out. So 85, write a proof in the style of your choice. Thank you. I don't know if I'm actually thanking them. I'm saying like, thanks. Kind of the pitch perfect. Thanks. Gosh, what's her name? Bella? Becca. Becca. I don't know if we learned her last name in that movie. Someone else is like, it's this. We have to learn her last name. Come on, what is it? Becca from Pitch Perfect. What is her last name? It's with a single C, right? B-E-C-A. All right. Given. All right, we're given two triangles are congruent already to start with. That's not a corollary. I thought we were proving the corollary at some point. Maybe not. Because I thought that was going to be pretty easy. Triangle XYZ is congruent to triangle XWZ. And then they give us another angle thing. Now, they're saying prove it's a rhombus. So, XYZ, I'm going to kind of plan some things out. XYZ is congruent to XWZ. Now, the order in which they say those matter. Corresponding parts of congruent triangles are congruent. So, I could state that this is congruent to this. Obviously, that's congruent to itself by reflexive property. That's good. I could state that this is congruent to this. We don't know anything about rhombus parallelogram. We can't use opposite sides, nothing like that. I can say that this is congruent to this. I can say that this is congruent to this. And then they're also going to talk about XYW and ZWY. XYW and ZWY. That'll give me opposite sides parallel for that bit. But I also have these ones here. So I can use CPCTC for... I'm going to do the side things. I wonder if I want sides or angles. That'd be an angle side side if I do that with those angles. Those would be parallel lines. Sorry, I'm planning some things out. Those would be parallel lines there. That's one set of opposite sides. Oh, but those aren't the same. Hold on. Boom. Boom. The diagonal here is drawn. Whether or not anything's marked, that diagonal is drawn. We'll get that that's congruent to that. We'll have an angle side angle case there, which is enough to do what? Sorry, I'm looking through this. That there of an angle side angle for triangle congruence, that triangle. Obviously, like I can do a lot off of that. I just want to do it faster. I want to see which parts I want by CPCTC here. Those are congruent. Diagonals bisect each other, and I could use the converse of that. Oh, prove it's a rhombus, not a parallelogram. Okay, so if I do that, I could do... Okay, I'll do the congruent angles and congruent side bits. And then I'll call that an angle bisector with those things congruent, which is fine. All right, let's try this. All right, we have that given. Let's also, let's put in the other given. Do I need it yet? I'll just put it in. I'm trying to think what I'm going to use it. XYW is congruent to ZWY. All right. Still given. Same given. Okay. Statement 2. Let's go with the markings I started to put in. Now I put in a lot of markings. I'm going to have to erase these ones. No, you know what? Leave them. That's part of the givens. But the segments that I just made here are also now congruent. And the angles, right? So I have a few of them. What do I have? This is all CPCTC, because triangles, they often don't start with given something's congruent. I don't think I need to do another triangle congruence part here, but here's a CPCTC I can work off of. YXZ, so I got YXZ here, and I'm going to do WXZ there. So two sets of angles there that are congruent. And then, kind of see all the rest when I say them out loud. Now I got YZX and then WZX. And then I got that XY with XW. And then I have YZ, boom, and WZ. And that's all CPCTC. So, whoopsie, a lot of CPCTC stuff there. So, with the angles congruent, I can say that those are angle bisectors. If I want to prove something's a rhombus, I can work off angle bisectors. I can work off of, just a lot of things there. So I can say that segment XZ was bisecting that angle where I marked those congruent. So XZ bisects both angles WXY and WZY. WXY and angle WZY. This is probably the thing I could have done a little bit more so. So definition of angle bisector. This is the thing I probably could have done more so on that one that I was lingering on for a while, because now that I have the bisector things, I can now start talking about the bigger angles that are congruent in some sort of ways. Like the X, let's see. Let me think about this one. Maybe not. I was saying I was going to make these congruent here, but I keep forgetting. It's a rhombus that I need congruent, not a parallelogram. Or I need to say it's a rhombus, not a parallelogram. So forget what I was going to say there. I have these given... Do I need to use the parallel lines thing? I'm not doing a parallelogram. Oh, you know what I can do? All right. This is an isosceles triangle. See, I would know this if I knew I had a rhombus, but we're proving we have a rhombus. But I have markings. Boom. I have an isosceles triangle. That means this is congruent to that, and we already know that that's congruent to this other thing, so we can use transitive property, and I have another one over here. So I don't know if I have to say it's an isosceles triangle. I feel like that would be a lot of things. I'd say these are congruent. It's an isosceles triangle. The definition of isosceles triangle, they have another name for those, so base angles, right? I think there's a theorem you can work off of that one straight up. So if I said angle, because otherwise I'm like, this is isosceles, this is isosceles. I'm gonna go straight into this. I'm gonna say angle, I got XWY, whoops, that should be a W. XWY is congruent to angle, now it's XYW. And then I can also do it for the bottom one. So ZWY, congruent to angle ZYW. Base angles of an isosceles triangle are congruent. Base angles of well, I never called an isosceles triangle. I was a base angles theorem. It's probably that name based off using that thing, because that's what isosceles triangles do. They would have proved that a long time ago. It must be a theorem. So now we got the transitivity property of congruence. Transitive property of congruence that now states that these other parts are congruent. So X, Y, W, they're drawn as such now. But now we can say that XYW is congruent to, see, I have to mark this one congruent here. XYW is congruent to WYZ, and XWZ is congruent to ZW, or XWY is congruent to ZWY. XYW congruent to angle ZYW. And angle XWY is congruent to angle ZWY by transitive property of congruence. Whew. And now that diagonal is bisecting those. So WY bisects angle XWZ and XYZ. By definition of angle bisector. And because we proved this before, it was the previous one. Now this is a rhombus because it's the converse. It's the rhombus's angle bisector converse. WXYZ is a rhombus. I forget its name. Rhombus. I'm making something up. Angle bisector converse. It's once I know that I have angle bisectors in there, then I know that it's a rhombus based off the quadrilateral stuff. Okay. Number 86. Write a proof in the style of your choice. How long have I gone so far? Past 3 hours. Okay. Never a fan. 86. Especially in the middle of the night. On my weekend. Times it. Oh boy. BC is congruent to AD. It's 6:23 in the morning. It's morning now. It's not middle of the night anymore. I started this in the middle of the night. BC is congruent to AD. Is this rectangle? Yeah, prove it's a rectangle. Okay, BC congruent to AD. BC perpendicular. Now they didn't show us markings this time. Now we have to do the markings for this one. And AD perpendicular to DC. Okay, these are given, and let's mark it as such. So BC and AD, boom. BC perpendicular to DC, boom. AD perpendicular to DC, boom. Prove it's a rectangle. I'm very much in the camp of wanting to use the, if these are both right angles, they're also supplementary to each other, the 90-degree things. And then we have it's the converse of the same side interior angle theorem, basically. That would make these lines parallel. And then we can use this is from section 7.3. It's a parallelogram based on this thing, and it's a right angle based on that. If we prove it's a parallelogram, I think we can work off some things with that, if that makes sense. Based off parallelogram, we can use the opposite sides parallel and congruent thing. You know what I mean? I don't know if I can use that theorem thing there. Or, well, that's why it's a parallelogram. But then after that, I have a right angle, therefore. Can I just say that? I think I have to do the opposite angles congruent, that kind of stuff. So here we go. Let's go with, now I overmarked those last parts, but those are givens. All right, so given there. Now we can say, okay, well now I'll mark that. I'll just say that these are now parallel. It's not about right angle stuff anymore. It's just, those are parallel. This is, well, that would be another theorem. Two lines perpendicular to the same line are parallel to each other. I forget what that one's called. But it is two, AD is perpendicular to BC. I don't want to do the whole they're right angles and then they add to 180 and stuff like that. AD is parallel to BC. I'm just going to explain it. It's same side interior angles converse, but this way, two lines perpendicular to the same line are parallel to each other. Perpendicular to same line. There's no reason why parallel to each other. There's no reason you're not allowed to give a reason as a sentence, as a statement. Like reflexive property, shared side in both things, Anyway, now that means that ABCD is a parallelogram. This is because of that name. I think it was opposite sides parallel and congruent theorem. Opposite sides parallel and congruent theorem. Okay. Now that it's a parallelogram, we can work off of the right angles that we still have. It's a parallelogram. opposite angles congruent here, like angle D, you know, those kinds of things. I guess. I don't know if that's really the way that you're going to say that, but I will. We'll go off of angle ADB, or ADC is congruent to angle CBA, and angle, excuse me, BAD is congruent to angle ADC. No, BAD, where was I? BAD and DCB. CB. Parallelogram opposite angles theorem. So let's mark those. Now, they're also right angles. Now, I never really said those other ones were right angles, right? I feel like I probably need to. So, angle D. I don't know. Can I just call it angle D? Do I have to do all these bigger ones? Or can I just... I don't think so, because the diagonals. So, they're right angles, yet at the same time, they're congruent. Here's the thing. If they're congruent, I can use transitive properties to congruent. I don't even have to state they're right angles. I guess for the rectangle. I guess I do. I also want to say angle ADC is congruent to angle... Somewhere I skipped the right angles part. I apologize. BCD. Those are congruent to each other. I could have said this a while back, but I was doing the parallelogram part first and spinning off that. Right angles theorem. All right angles are congruent. You know what? I probably do need... I can't just say skip it. This isn't just for me. This is also for you. Step 5 will be that they're right angles by definition of perpendicular lines. Angle A, D, C, and angle B, C, D are right angles. Definition of perpendicular lines. And now they're congruent to each other by the right angles theorem. Okay, if they're congruent to each other, then by transitive property, they're kind of all congruent to each other. So I could now state, like, so ADC was to CBA. What's CBA? So ADC. So ADC is CBA. So CBA. Well, now I can say those others are right angles. Also right angle theorem. CBA and angle, what is it, BAD, are right angles. Are rights. They're rights. Right angle theorem again. Maybe the converse. All right angles are congruent. All congruent right angles are right angles with each other. And 8, ABCD is a right angle by its definition. It's a right angle. It's a rectangle, not a right angle. Rectangle. I was going to say definition of right angles. Definition of rectangles. Whew. All right. One more. Oh, two more. Two more problems. All right, number 87. Given it's a rectangle, prove the diagonals are congruent. So I'm going to draw, because there's no rectangle drawn. I'll probably draw it on this side. Let me build that up. Let's build it up. So what can we use about the rectangle? We can use the right angles congruent. We can probably state opposite sides. See, we can use anything that a parallelogram can use. A parallelogram does not have congruent diagonals by nature, but it has opposite sides congruent by nature. So with PQRS, here's the thing. I'm only going to focus on 2 sets of things, really, I think. Well, no, I need all diagonals congruent. We'll see. But I have a plan in mind. My plan is kind of like this. I want to do kind of like that this big triangle right here is congruent to this big triangle right here. And then I'm going to use CP/CTC to say that those two things are there. I think that's fine. So I think this is kind of going to be a shorter proof. I don't know what the last proof is about yet. Okay, 87. Statements, reasons. All right, statement 1, PQRS is a rectangle. Okay, so angle P and Q, well, now I got to call them the big guys. Angle SPQ and angle RQP are right angles. I'm actually not going to worry about the other ones being right angles. I'm just going to choose 2 of them. Definition of rectangle. Now, therefore, those 2 are also congruent to each other by right angle theorem. Angle SPQ is congruent to angle RQP. And these letters I use are important as far as like, these are the letters I'm using in the triangles. And I can use them in that way as well. Right angle theorem. Okay, so I have 2 congruent angles there. Let me actually get rid of these other ones here. I'm not going to use them. I have no plan of using them. So now remember the triangles I'm working off of. I can say segment SP is congruent to segment RQ. Opposite sides of a parallelogram are congruent. Opposite sides of a rectangle are congruent. I can probably say the parallelogram one. I don't think I need to state it's a parallelogram beforehand. Maybe I do, but I'm not. Parallelogram opposite sides theorem. It's a parallelogram because rectangles are parallelograms. I just don't think that's a reason I've ever stated before. PQ is congruent to QP itself. It's the shared side. That's a reflexive property. PQ congruent to QP. And the only reason I changed that is because these are reflected drawings. Reflexive property. Okay. The triangles are now congruent by side angle side. Now keep in mind what 2 triangles I'm looking at, because I'm 3 steps away from the answer. No, 2 steps. So here, this triangle is congruent to, let's use a different color. Here, this triangle. This is going to be a side angle side case. And I can use the triangle, I can use the letter order I've been using because I've been trying to correspond parts this entire time. So triangle SPQ is congruent to triangle RPQ, or RQP. RQP by side angle side. And finally, we can say the PR is congruent to SQ by CPCTC. Okay. 7 steps, not bad. And the last one we have is number 88. Given PQRS is a parallelogram, prove PQRS is a rectangle. Okay, so this is going kind of the other way, I guess. Not really. Oh, P and PR is congruent to SQ. Okay, that's also another thing. I was going to say, how do I prove a parallelogram is a rectangle? With the congruent diagonals, we can apparently do that. So let's look into it. Let's change that into that. I don't get sleep after either. I got softball pretty much the rest of the day. Okay. Okay, being a parallelogram and the congruent diagonals, and they got both diagonals congruent, so I don't know where I can work out that. You can either use alternate interior, I'll probably do the alternate interior angles. You could use opposite sides congruent, side, side, side. You have a bunch of options there. But with the congruent diagonals, I wonder I can build off of that to state maybe certain triangles are congruent. Maybe I can do the same thing on the congruent triangles and do these two, like going across. Like, again, SPQ and RQP. If I do those two congruent, then those two angles congruent by CPCTC, and then opposite angles are congruent. I can probably do something off that. So let's see. If I have, I'm going to kind of mark some things up before I start. If I have these two congruent, boom, boom, like that. Opposite sides congruent in a parallelogram. I can still use that. Reflexive property. I'll have a side-side-side case. Then I can say this angle congruent to this angle by CPCTC. They're not yet right angles, but they will be. Congruent by CPCTC. And they're supplementary. They add to 180. And linear pair supplementary angles that are congruent are also right angles. And then opposite sides or opposite angles congruent. I think I'll do that. All right, so that's my plan here. Okay. So let's start with this. Let's start with the givens. PQRS is parallelogram. Da 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 da. And PR is congruent to SQ. All right, 2, dos. Scarretos. PS congruent to RQ, what I put up, or SP congruent to RQ. Opposite sides, parallelogram, opposite sides theorem. PQ congruent to QP, reflexive property. Reflexive property. So these two triangles are once again congruent. So I got triangle SPQ congruent to triangle RQP by side this time. Okay, now within those two triangles, remember I have a triangle here and a triangle here, right? Those are very, very terrible markings. So this angle is congruent to this angle by CPCTC in both those triangles. We don't know the right angles yet. And I wonder how I want to list that out, but angle, without getting too technical. Angle SPQ is now congruent to angle RQP by CPCTC. Now, I just want to say the opposite angles are congruent. I can do consecutive angles supplementary, and then they add to one. There's got to be a fast way to say that right angles, that they make right, that they're perpendicular, all that kind of stuff. Parallel. Maybe I can do the opposite of what I did here on that one problem. If two angles, I don't want to do like 7 steps to write this thing out. There's got to be a fast way for me to say that. You know what? Maybe there isn't. Maybe I just have to go. Maybe I just have to jump into it. Maybe there's no theorem. Let's just go straight into it. Let's say if they're congruent, their measures are equal. By definition of congruence. Okay. So if their measures are equal, basically what I'm going to do is talk about how they add to 180, like all that kind of stuff, right? They add to 180, and then, and you know what? Maybe I can get the other, I can probably get the other angles with this after. So SPQ is equal, plus measure of angle RQP equals 180. This actually can maybe work in its favor, because same parallel lines supplementary, same side interior angle theorem. Well, no, the supplementary angles, parallelogram, consecutive angles theorem. Let's work off it that way, not same side interior. Now, if we have those, I can probably do this. If I can state they add to 180. I can do a substitution. I can have one take place of the other and just say it's 90. Here, I can do both of them. I can make sure they're both 90 at the same time. SPQ can take RQP's place because boom, and RQP can take SPQ's place. At the same time, I can make them both right angles. So two SPQs would be 180. Two RQPs would be 180. Substitution property of equality. Okay, so from there I can divide these by 2. Measure of angle SPQ is 90. Measure of angle RQP is 90 degrees, right? That is division property of equality. $90 degrees, they're right angles by definition of right angles. See, this is things I wanted to save doing all these steps. Angle SPQ and angle RQP are right angles by definition. Sorry. Definition of right angles. Can I just go straight to all the other ones are... Okay, so there's all that. These other ones from way back, CBCTC, great. From them being congruent, sorry, from this being a parallelogram. This is a parallelogram, so opposite angles are congruent. Now I think I can finally jump over to that area. Let's call that PSR. So by the way, based on my drawing, I lost my drawing here. Based on my drawing, these are now right angles. Now right angles. Now I'm going to say how these are congruent to each other. That congruent to that congruent to that as opposite angles. So that's PSR and QSR. So 11. Angle PSR congruent to angle QSR. That's the parallelogram opposite angles theorem. Measure of angle PSR is congruent to, or equal to measure of angle QSR. And that's definition of congruence. See, this is a lot, man. Definition, see, this is why people hate geometry. They hate proofs. 13, now these are 90 degrees. By substitution. Transitive property? I think here I get to say transitive property instead of substitution. Transitive property of equality. Sorry for the handwriting. I'm saying it out loud. 14. Now they're right angles. Angle PSR and angle QSR are right angles. I always write things the same way here. Definition of right angles. And finally, PQRS is a rectangle by definition of rectangle. Okay, y'all, I am checked out. I should be much more professional than that. I don't care. Guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Here is almost 3.5 hours. Oh, that guy's down for the count. Let's go. That is me. And that is math. that just kicked my behind. You guys probably didn't get to watch any of these ones here. Stay tuned for whatever else I record after. Check the playlist and all that kind of stuff, guys. This is Mr. Robinson. Thank you so much for watching, because I'm not doing this for myself. Take care. I will see you in the next one.